The universe has always been a grand stage of the unknown, filled with wonders so strange they defy our very understanding of reality. Picture a catalogue not of books or artifacts, but of celestial enigmas, each entry more baffling than the last, lurking in the depths of space. This is the new General Catalogue, or NGC, a treasure map to the cosmos that astronomers have relied on for over a century. But hidden within its pages are objects so peculiar, so utterly unexpected, they challenge everything we think we know about the night sky. What if I told you some of these cosmic oddities shouldn't even exist? Galaxies that spin backwards, stars wrapped in mysterious dark matter halos, and nebulae that glow with colors unseen anywhere else in nature. The NGC isn't just a list, it's a gateway to the universe's best-kept secrets, and today we're diving deep into 50 of its most mind-bending entries. These aren't just distant points of light, they're cosmic anomalies that push the boundaries of physics, leaving even the brightest scientists scratching their heads in awe. This journey isn't just about stargazing, it's about uncovering the stories behind these celestial rebels. How did they form? Why do they behave in ways that defy all logic? And what can they teach us about the hidden forces shaping our universe? From ghostly remnants of dead stars to galaxies that seem to dance in defiance of gravity, each of these 50 objects holds a clue to the grand puzzle of existence. So buckle up. By the end of this exploration, you'll never look at the night sky the same way again. Deep in the heart of the Perseus Cluster, some 230 million light-years from Earth, lurks a cosmic beast with an insatiable appetite, NGC 1275. This isn't your typical galaxy. At its core sits a supermassive black hole, not just resting quietly but erupting in a frenzy of activity, spewing out jets of plasma at nearly the speed of light. These aren't gentle streams, they're violent, twisting tendrils stretching tens of thousands of light-years into space, glowing fiercely in radio waves and X-rays. But here's where it gets even stranger. Surrounding NGC 1275 is a vast sea of superheated gas, so dense and turbulent it defies expectations. Astronomers call this a cooling flow, a term that sounds peaceful but hides a paradox. The gas should be cooling down and collapsing inward, fueling new stars. Yet somehow it doesn't. Instead, the black hole's eruptions act like a cosmic thermostat, reheating the gas in a feedback loop that scientists are still struggling to fully explain. It's as if the galaxy itself is fighting against its own demise, refusing to let its gas settle quietly into star formation. What makes this monster even more fascinating is its radio emissions. The jets aren't just chaotic, they're structured in a way that suggests hidden magnetic forces shaping their paths, like invisible hands molding the eruptions. Some researchers think these jets could be the key to understanding how black holes regulate entire galaxy clusters, acting as the ultimate puppet masters of their cosmic neighborhoods. And then there's the mystery of the gas filaments, delicate, thread-like structures weaving through the chaos, glowing in eerie blue light. These filaments shouldn't survive in such a violent environment, yet they persist, hinting at forces still unseen. Are they remnants of past collisions, or perhaps the result of some unknown magnetic phenomenon? Every observation of NGC 1275 seems to raise more questions than answers, making it one of the most compelling enigmas in the NGC catalogue. This isn't just a galaxy, it's a cosmic laboratory, a place where the universe tests the limits of physics right before our eyes. And as we keep watching, who knows what other secrets this monster might reveal. Stretching across 20,000 light-years like ghostly bridges suspended in the void, the filaments of NGC 1275 are one of the most haunting cosmic puzzles ever observed. These delicate tendrils, some no wider than a few hundred light-years, glow an ethereal blue ionized gas threaded through space as if woven by unseen hands. Their very existence defies logic. In the maelstrom surrounding the galaxy's supermassive black hole, where temperatures soar to millions of degrees and plasma jets roar at relativistic speeds, such fragile structures should have been ripped apart instantly. Yet here they are, enduring against all odds for tens of millions of years. Theories abound about their origins, but two stand out. One suggests these filaments are cosmic relics, remnants of gas stripped from other galaxies during violent collisions, stretched thin by tidal forces and set alight by the black hole's radiation. Imagine a spiderweb caught in a hurricane, somehow holding its form as the storm rages around it. The other theory points to magnetism's invisible grip. Powerful magnetic fields twisted by the black hole's energy might be channeling the gas into these narrow streams, shielding them from destruction like electromagnetic armor. Recent observations hint at this possibility, detecting faint magnetic signatures threading through the filaments like hidden reinforcement cables, but the mystery deepens when you examine their temperature. While the surrounding intracluster medium burns at millions of degrees, the filaments hover around a mere 10,000 degrees, relatively chilly by cosmic standards. How do they stay so cool amidst such infernal heat? Some researchers propose rapid cooling mechanisms, where dense pockets of gas radiate energy away faster than their surroundings can heat them. Others speculate that magnetic fields not only shape the filaments but insulate them, creating pockets of order within the chaos. Perhaps the most astonishing detail is their structure. Unlike random cosmic debris, many filaments exhibit eerie symmetry, aligning along the galaxy's radio jets or forming intricate loops. One particularly striking formation resembles a helix, spiraling through space as if sculpted by a deliberate force. Could this be evidence of large-scale magnetic fields organizing matter across galactic distances? Or are we seeing the aftermath of some cataclysmic interaction frozen in time? What makes these filaments truly extraordinary is their broader significance. If magnetic fields are indeed preserving them, it would imply that such forces play a far greater role in shaping galaxy clusters than previously thought, not just as bystanders but as active architects of cosmic structure. Alternatively, if they're the shredded remnants of past collisions, they could reveal how galaxy clusters cannibalize their neighbors over eons. Either way, NGC 1275's filaments aren't just celestial curiosities. They're a window into the forces that weave the universe's grand tapestry, one thread at a time. NGC 5128, better known as Centaurus A, isn't just another galaxy, it's a cosmic battlefield. A sprawling testament to violence and rebirth, this giant elliptical galaxy bears the scars of a cataclysmic collision that reshaped its very identity. What sets it apart is the thick, jagged dust lane slicing across its center like a wound that never fully healed. This dark, chaotic belt isn't just debris, it's the mangled remains of a smaller spiral galaxy devoured hundreds of millions of years ago, torn apart by gravitational forces and woven into Centaurus A's fabric. But the drama doesn't stop there. At its heart lurks a supermassive black hole 55 million times the mass of our Sun, spewing twin jets of plasma at nearly the speed of light. These aren't subtle wisps, they stretch over 1 million light-years into intergalactic space, visible only in radio waves, painting the sky with invisible fire. What's baffling is their trajectory. Unlike the neat, straight jets seen in many active galaxies, Centaurus A's are warped, twisting as if caught in some unseen cosmic current. Astronomers suspect this distortion is a lingering echo of that ancient merger, the black hole's spin knocked off kilter by the galactic carnage. The dust lane itself is a puzzle. Most elliptical galaxies, having exhausted their gas and dust long ago, appear smooth and featureless, yet Centaurus A flaunts this dark, messy streak like a badge of defiance. Infrared observations reveal it's not just a passive remnant, it's a breeding ground for newborn stars ignited by shockwaves from the merger. Somehow, amid the chaos, pockets of gas collapsed into stellar nurseries, proving that even destruction can spark creation. Then there's the galaxy's radio roar. Centaurus A is the closest active radio galaxy to Earth, its jets pumping out enough energy to outshine entire star systems. Researchers believe these jets might be responsible for another oddity: vast bubbles of ultra-hot gas ballooning from the galaxy's core, visible in X-rays. These so-called Fermi bubbles suggest the black hole's outbursts aren't just local, they're shaping the galaxy's surroundings on a colossal scale. But perhaps the most tantalizing question is what's hidden beneath the dust. Recent studies using submillimeter telescopes have detected strange, fast-moving gas clouds near the core clumps, hurtling at thousands of kilometers per second, possibly flung outward by the black hole's fury. Some even show signs of complex organic molecules, hinting that the raw ingredients for life might survive even in these extreme conditions. Centaurus A is more than a relic of the past. It's a living laboratory, a place where the aftermath of a cosmic crash continues to unfold. From its warped jets to its star-forming scars, every detail whispers the same truth: in the universe, chaos and beauty are forever entwined. If Centaurus A's warped jets are the sparks, its radio lobes are the inferno-colossal structures spanning over 1 million light-years, dwarfing the galaxy itself. These faint, ghostly bubbles of energy stretch far into intergalactic space, invisible to the naked eye but blazing in radio wavelengths. They're not just remnants, they're active proof of the galaxy's explosive past, pressurized by the supermassive black hole's relentless outbursts over tens of millions of years. What's staggering is their scale. Imagine a structure so vast it could swallow our Milky Way and Andromeda side by side with room to spare. The lobes aren't static, they're dynamic, filled with magnetized plasma ejected at nearly light speed. As particles spiral along magnetic field lines, they emit synchrotron radiation, creating a diffuse glow detectable across the universe. But here's the twist: these lobes aren't symmetrical. The northern lobe appears brighter and more structured, while the southern one fades into a wispy haze. This lopsidedness hints at an uneven distribution of intergalactic gas, or perhaps variations in the black hole's feeding cycles. Digging deeper reveals another layer of mystery. Filaments and knots within the lobe's regions of intensified emission suggest turbulent substructures like cosmic eddies in a river of energy. Some researchers propose these are shock waves from older outbursts, frozen in time as new material piles up behind them. Others argue they're evidence of magnetic reconnection, where field lines snap and realign, releasing bursts of energy. Either way, these features transform the lobes from simple cavities into intricate records of the galaxy's violent history. Then there's the question of impact. These lobes aren't just celestial graffiti, they're reshaping their surroundings. By pushing against the thin gas between galaxies, they create pressure waves that could stifle star formation in nearby dwarf galaxies, or even regulate the flow of matter into the larger cluster. It's a feedback loop on a cosmic scale, the black hole's fury altering the environment that feeds it. But the real enigma lies in their longevity. How do these structures persist for so long without dissipating? Simulations suggest magnetic fields act like cosmic scaffolding, preventing the lobes from collapsing or mixing with the surrounding medium. That means Centaurus A isn't just a local spectacle. It's a case study in how galaxies communicate with the void, etching their stories into the fabric of space itself. These lobes are more than relics, they're a living testament to the universe's unyielding energy, a reminder that even in the darkest reaches, violence and beauty are written in radio waves. Nestled in the constellation Monoceros, NGC 2264 sparkles like a celestial holiday display, earning its nickname, the Cosmic Christmas Tree, with good reason. This dazzling star-forming region is a riot of color and motion, where newborn stars blaze to life amidst swirling clouds of gas and dust. At its heart stands the iconic Cone Nebula, a towering pillar of darkness 7 light-years tall, its silhouette carved by the fierce stellar winds of young, massive stars. This isn't just a static snapshot, it's a dynamic nursery where gravity and radiation wage an eternal tug of war, shaping the cosmos in real time. What makes this tree truly glow is the brilliant variable star S Monocerotes, a luminous giant flickering at the cluster's core. Unlike most stars, S-Mon's brightness isn't constant. It pulses unpredictably, casting shifting illumination across the nebula like twinkling lights on a cosmic fur. Surrounding it, a flock of hot, young stars, some barely a few million years old, sculpt the gas into ethereal ribbons and cavities, their ultraviolet light ionizing hydrogen into vibrant reds and blues. The result is a scene of festive chaos where creation and destruction dance hand in hand. But the real magic lies in the details. Infrared observations reveal hundreds of protostars buried deep within the nebula's dusty folds, each one a potential solar system in the making. Some are ejecting colossal jets of material, visible as Herbig-Haro objects, those fleeting, glowing streaks that mark a star's violent birth cries. And then there's the Snowflake Cluster, a geometric array of stellar newborns arranged in near-perfect symmetry, as if nature itself decided to hang ornaments on this cosmic tree. Yet the Cone Nebula steals the show. Its stark, angular profile defies the soft curves typical of most nebulae, standing like a monolithic spire against the stellar fireworks. Simulations suggest its peculiar shape comes from a delicate balance. Radiation from nearby stars erodes the gas cloud while magnetic fields channel the flow, creating this startlingly sharp silhouette. It's a reminder that even in the vastness of space, physics can carve structures of startling precision. The cosmic Christmas tree isn't just a pretty sight. It's a classroom. By studying its stellar demographics from fledgling protostars to the volatile S-Mon, astronomers piece together the life cycle of star clusters. Why do some stars form in tight knots while others scatter? How does radiation from massive stars influence their smaller siblings? Every glimmer in this galactic grove holds clues, making NGC 2264 not just a holiday spectacle, but a gift to science itself. NGC 3242, known as the Ghost of Jupiter, floats in the night sky like a celestial phantom, a glowing orb so vivid early astronomers mistook it for the gas giant itself. But this is no planet. It's the final breath of a star, a planetary nebula where a dying sun has cast off its outer layers in a last violent sigh. The nebula's haunting greenish-blue glow comes from ionized oxygen and nitrogen, energized by the ultraviolet radiation of the white dwarf at its heart. What makes this cosmic specter truly mesmerizing is its structure, not one, but two distinct shells of gas expanding into space like nested spheres. The inner shell gleams with turbulent knots and intricate filaments, while the outer one stretches farther, fainter, a ghostly echo of the star's earlier eruptions. At the center lies the star itself, a white dwarf hotter than 30,000 degrees Celsius, its intense radiation stripping electrons from the surrounding gas and making it fluoresce. But this isn't a peaceful retirement. Observations reveal the star is spinning rapidly, its rotation possibly accelerated by unseen companion stars or swallowed planets. Some researchers even speculate the complex shapes of the inner shell, those twisted loops and braids, could be signs of magnetic fields sculpting the outflow, like invisible hands molding smoke. Then there's the mystery of the outer shell. While most planetary nebulae exhibit a single, cohesive structure, the ghost of Jupiter's faint outer halo suggests multiple episodes of mass loss. It's as if the star experienced violent convulsions long before its final death throes, shedding material in fits and starts over millennia. Infrared images reveal dust grains mixed into this outer shroud, debris from the star's cooler, earlier phases, cosmic breadcrumbs tracing its evolutionary path. But the real enigma lies in the nebula's asymmetry. Unlike the perfect rings of some planetary nebulae, This one's inner shell is slightly elongated, with brighter regions hinting at colliding winds or uneven ejection. One theory suggests the dying star's intense magnetic field funneled material outward in jets, creating this lopsided glow. Another proposes the influence of a binary companion, its gravity tugging the expelled gas into unexpected shapes. What makes the ghost of Jupiter extraordinary isn't just its beauty, it's the story it tells. Every ripple in its gas, every twist in its structure, is a page in the diary of a star's demise. And as we study its glow, we're not just watching a cosmic ghost, we're witnessing the fate that awaits our own sun, a reminder that even stars must one day fade, leaving behind only their luminous echoes in the dark. NGC 6543, the Cat's Eye Nebula, stares back at us like a cosmic feline, its hypnotic rings and twisted tendrils telling a story of stellar death unlike any other. This isn't just another planetary nebula, it's a layered masterpiece with 11 distinct concentric shells of gas expanding outward like ripples in a pond. Each shell is a timestamp, a frozen echo of the dying star's final 1,000 years when it pulsed in rhythmic agony, ejecting material in violent bursts. The precision of these rings is staggering, spaced almost evenly, as if the star itself kept cosmic time, but the real mystery lies at the nebula's heart. Hubble's sharp gaze reveals a chaos of knots, jets, and braided filaments, all swirling around a central white dwarf. This intricate structure defies simple explanations. While most planetary nebulae form smooth, symmetrical shapes, the Cat's Eye is a turbulent storm of activity, the leading theory a binary companion. Imagine a dance of death, two stars entwined, one shedding its outer layers while the other's gravity sculpts the expelled gas into these surreal shapes. Some astronomers even suggest the companion might have plunged into the dying star's envelope, spiraling inward and whipping up the gas like a celestial mixer. Then there's the matter of speed. The nebula's outer shells drift outward at a leisurely 50 kilometers per second, while the inner structures race at over 1,000, a disparity that hints at multiple eruptive phases. Spectroscopic studies reveal shocks within the gas, evidence of violent collisions between fast-moving material and slower, older ejecta. It's as if the star didn't die quietly but in a series of explosive tantrums, each outburst leaving its mark. What makes the Cat's Eye truly unique is its chemical fingerprint. Unlike most planetary nebulae rich in hydrogen and helium, this one's outer shells are strangely nitrogen-heavy, a clue that the star might have been massive enough to fuse elements deep in its core before shedding its skin. Meanwhile, the inner regions glow with forbidden lines of oxygen and neon, their eerie green light a testament to extreme conditions. Perhaps most haunting of all are the ANSI, two faint, symmetrical flares extending from the nebula's sides like outstretched wings. These aren't random features, they're likely bipolar jets launched along the star's rotation axis during its death throes. Their persistence suggests the white dwarf's magnetic field, still potent even in death, is channeling leftover energy into space. The Cat's Eye doesn't just challenge our understanding of stellar demise, it redefines it. Here, in this tangled web of gas and light, we see a star's death not as an end but as a metamorphosis. And as we unravel its secrets, we're reminded that even in destruction, the universe creates beauty beyond imagination. NGC 7027, nicknamed the Jewel Bug Nebula, defies all expectations of what a dying star should look like. Unlike the graceful rings of the Cat's Eye or the symmetrical shells of the ghost of Jupiter, this planetary nebula presents itself as a jagged, almost rectangular ember glowing in the constellation Cygnus. Its edges are sharp, its corners abrupt, as if the cosmos took a pair of scissors to a cloud of gas and trimmed it into a geometric masterpiece. But this isn't the work of stellar origami. The nebula's bizarre shape is the result of an all-out war between radiation and dust, a battle so intense it's rewriting the rules of how stars expire. At the heart of this cosmic jewel lies a white dwarf hotter than most, its surface blazing at nearly 200,000 degrees Celsius, pumping out ultraviolet radiation with enough ferocity to ionize the surrounding gas into a kaleidoscope of colors. The nebula's outer layers, rich in complex carbon molecules and dust, glow in vivid greens and blues under this relentless assault. But what's truly baffling is the structure of those layers. Hubble images reveal concentric dust shells, each one etched with intricate, maze-like patterns, as if the star's death throes were transcribed in hieroglyphs of soot and starlight. Then there's the matter of speed. Jewel Bug is one of the youngest known planetary nebulae, with an estimated age of just 600 years, a blink in cosmic time. Yet its gas is racing outward at over 30 kilometers per second, propelled by shock waves from the central star's explosive transition. This isn't a slow unraveling, it's a stellar tantrum of epic proportions. Spectroscopic studies show the nebula is even surrounded by a faint halo of material ejected tens of thousands of years earlier, proof that the star began shedding its skin long before its final, violent outburst. But the real enigma is that rectangular silhouette. Most planetary nebulae form spheres or hourglasses, shaped by their star's rotation or binary companions. Jewel Bug's crisp angles, however, suggest something far stranger. One theory points to an exceptionally dense equatorial disk of dust, so thick that the star's radiation can only escape through polar openings, carving the gas into this box-like form. Another idea involves magnetic fields, invisible lines of force channeling the outflow into rigid structures, like a cosmic cookie cutter pressing into the nebula's soft glow. Perhaps the most startling discovery, though, lies hidden in the dust itself. Observations from the James Webb Space Telescope reveal the presence of complex organic molecules, including polycyclic aromatic hydrocarbons, the same compounds found in soot and interstellar clouds. How these fragile molecules survive the star's scorching ultraviolet barrage is a mystery. Some scientists speculate they're shielded within dense clumps of material, like cosmic bunkers weathering a radiation storm. Others wonder if they're reforming continuously, assembling themselves anew even as the star's fury tears them apart. The Jewel Bug Nebula isn't just a spectacle. It's a laboratory for extreme physics, where dust defies annihilation and geometry bends to unseen forces. Every strange facet of this cosmic gem challenges our understanding of stellar death and hints that the universe's rulebook might be far stranger than we ever imagined. NGC 6888, or the Crescent Moon Nebula, isn't just another glowing cloud in space. It's the aftermath of a stellar hurricane, a cosmic storm front sculpted by one of the universe's most extreme stars. At its heart lies WR136, a wolf-rayet star so ferocious it makes ordinary supergiants seem tame. This isn't a star gently burning through its fuel. It's a celestial blowtorch, shedding entire suns' worth of mass in a relentless gale of stellar wind. Every second, WR136 hurls out material at over 2,000 kilometers per second, fast enough to cross the continental United States in the blink of an eye. That's 1,000,000 times fiercer than our own sun's solar wind, and it's this violence that carves the nebula's haunting crescent shape. Unlike the delicate shells of planetary nebulae, the crescent moon is a churning battlefield. The nebula's glowing tendrils aren't just expelled gas, they're the shock fronts where WR136's hurricane force winds collide with slower material the star ejected earlier in its life. Picture a snowplow ramming through a drift, compressing and heating the snow until it glows. That's exactly what's happening here, except instead of snow, it's interstellar gas superheated to millions of degrees, emitting intense X-rays alongside its visible glow. The result, a bubble expanding into space, its edges shimmering with turbulent energy. But there's a twist. The crescent moon isn't a perfect sphere. Its namesake shape comes from a lopsided distribution of gas, thicker and brighter on one side where the stellar winds plow into denser remnants of the star's past outbursts. Infrared observations revealed dust mixed into these regions, debris forged in the star's own furnace and then blasted outward. Even more intriguing are the finger-like protrusions dotting the nebula's surface, likely caused by instabilities as the shockwave rips through uneven clumps of material. It's as if the star's death throes are frozen in mid-eruption, a snapshot of chaos frozen in time. The real shocker, though, is the nebula's age. While most stellar bubbles fade over hundreds of thousands of years, the crescent moon is a relative infant just 70,000 years old. That's younger than human civilization, a blink in cosmic terms. Yet in that short span, WR136 has already shed enough material to form 15 suns. And it's not done. Spectroscopic studies show the star's outer layers are now so stripped away that its bare helium core is exposed, burning at temperatures exceeding 120,000 degrees. This is a star on the brink, poised to detonate as a supernova within the next million years. What makes the crescent moon truly extraordinary is what it teaches us about stellar life cycles. Wolf-rayet stars like WR136 are rare. Less than 1% of all massive stars reach this volatile phase. By studying how their winds sculpt nebulae, astronomers piece together how these cosmic titans enrich the universe with heavy elements. Every atom of oxygen, silicon, and iron in the crescent moon's swirling gases was forged in the star's core, now being sown into space where it might one day form new stars, planets, or even life. So when you gaze at this celestial crescent, you're not just seeing a pretty nebula. You're witnessing a star's furious last act, a preview of the supernova to come, and a reminder that even destruction can forge beauty on the grandest scales. NGC 2392, famously known as the Eskimo Nebula, looks like a celestial face peering through the frosty depths of space, its intricate Parker hood of gas swirling around a central star with uncanny symmetry. But this isn't just a pretty cosmic portrait. The nebula's fur-lined appearance hides a tempest, a storm of stellar winds so violent they've torn through the star's outer layers, sculpting one of the most complex gas structures ever observed. At the heart of this cosmic spectacle lies a dying star, its core exposed as a white dwarf blazing at nearly 50,000 degrees Celsius. The radiation it emits is so intense, it's shredding the surrounding gas into glowing filaments and knots, creating the illusion of a fur-lined hood. Hubble's razor-sharp images reveal these filaments in stunning, detailed, delicate loops and braids that look almost woven, stretching over a light year across. But what's astonishing isn't just their beauty, it's their speed. The central star's winds are racing outward at over 1 million kilometers per hour, slamming into slower-moving gas ejected earlier in the star's death throes. The collision is so violent, it superheats the material, making it shine in vivid blues and greens, oxygen and nitrogen ionized by the star's merciless ultraviolet glare. The real mystery, though, lies in the nebula's bipolar structure. While the outer hood appears spherical, closer inspection reveals a chaotic inner disk, tilted at an angle, with jets of material spewing from the poles. This isn't random chaos, it's evidence of a hidden cosmic dance. Most astronomers agree the star's spin, or possibly the gravitational tug of an unseen companion, has funneled the outflows into these opposing streams, creating a lopsided explosion frozen in time. But the Eskimo Nebula has another secret, its cometary knots. These are dense, teardrop-shaped clumps of gas, each one larger than our solar system, strewn throughout the outer shell. Like cosmic tadpoles, they sport glowing heads and streaming tails, all pointing radially away from the central star. These aren't just debris, they're survivors. Despite the hurricane-force winds, their sheer density shields them from complete disintegration, leaving behind these eerie, sculpted remnants. Some even contain the seeds of future molecules, carbon, hydrogen, and other raw materials that might one day be recycled into new stars or planets. What makes this nebula truly special is its age. At roughly 10,000 years old, it's a mere infant in planetary nebula terms, giving astronomers a front-row seat to the early stages of stellar death. The intricate patterns in its gas, the braids, the knots, the polar jets are like a fossil record, preserving the star's final violent eruptions in exquisite detail. And as we study its turbulent winds and twisted geometry, we're not just looking at a dying sun. We're witnessing the universe's relentless creativity turning destruction into art, one gust of stellar wind at a time. NGC 6302, the Butterfly Nebula, spreads its wings across space with an elegance that belies the violence of its birth. This isn't just another planetary nebula, it's a cosmic metamorphosis in action, where a dying star has erupted into a breathtaking display of symmetry and chaos. What catches the eye first are the two vast lobes, each stretching over 2 light years, glowing in hues of blue and red as they expand into the void. But these aren't gentle wisps of gas, they're superheated jets racing outward at over 600 kilometers per second, sculpted by forces so extreme they defy imagination. At the heart of this celestial butterfly lies one of the hottest white dwarfs ever discovered, a stellar remnant burning at over 250,000 degrees Celsius, so energetic it outshines entire galaxies in ultraviolet light. Yet for decades, this star remained hidden, cloaked in a thick torus of dust and molecules that absorbs nearly all its visible light. It wasn't until infrared telescopes pierced this dark veil that astronomers glimpsed the true engine behind the nebula's beauty. The dust isn't just a shroud, it's a key player in the drama, funneling the star's dying breaths into those magnificent bipolar jets like a cosmic nozzle. What makes the butterfly truly astonishing is the chemistry at work. Spectral analysis reveals its wings are rich in complex hydrocarbons, water ice, and even carbonates, materials you'd expect in planetary atmospheres, not the crucible of a dying star. Somehow, amid temperatures that should vaporize molecules instantly, these compounds persist, clinging to dust grains in the nebula's cooler outer regions. Even more perplexing are the crystalline silicates found in its dusty waste, minerals that typically form in the slow chill of planetary disks, not the maelstrom of stellar death. Then there's the matter of shape. Most bipolar nebulae form gentle hourglasses, but the butterfly's wings are riddled with intricate substructures, knots, filaments, and even shock-heated bubbles where the jets plow into older ejecta. Hubble's images reveal fine details resembling cellular membranes or spiderwebs, patterns that hint at magnetic fields or instabilities shaping the outflow. Some researchers propose the central star might be part of a binary system, its companion's gravity sculpting the gas into these precise forms. Others point to the star's rapid rotation, its spin flinging material outward like a cosmic sprinkler. But the real spectacle lies in the wing's temperature gradient. While the outer edges glow at a cool 10,000 degrees, the innermost regions near the star reach mind-bending temperatures, hot enough to tear electrons from iron atoms. This extreme range creates the nebula's striking color, contrast the blues of ionized oxygen near the center, fading into the reds of nitrogen farther out. It's a thermal masterpiece painted across light years of space. What makes NGC 6302 extraordinary isn't just its beauty, it's the unanswered questions. Why does its dust torus tilt at such a sharp angle to the jets? How do complex molecules survive in this inferno? And what cataclysmic event triggered such a perfectly symmetrical explosion? Every observation peels back another layer, revealing a stellar death more complex and wondrous than we ever envisioned. The Butterfly Nebula isn't just a celestial object, it's a reminder that even in their final moments, stars can create art on a galactic scale. NGC 5189 isn't like other planetary nebulae. While most of these dying star remnants form elegant spheres or tidy hourglass shapes, this cosmic spectacle twists through space like a frozen spiral galaxy, its S-curved arms stretching over 3 light years, glowing with an eerie green-blue radiance. At first glance, it looks like a celestial serpent coiled around its creator, a white dwarf star burning at the center. But this sinuous beauty isn't just random chaos, it's the smoking gun of a hidden stellar tango, a gravitational waltz so precise it's left its mark on the very fabric of the nebula. The secret to this spiral lies in duality. Most astronomers agree NGC 5189's hypnotic shape stems from a binary star system, where two stars orbit each other in a tight, rhythmic embrace. As the primary star swelled into a red giant and began shedding its outer layers, its companion's gravity tugged at the ejected gas, sculpting it into those sinuous arcs we see today. Imagine a garden sprinkler twisting back and forth, each oscillation imprinting a new curve in the outflow. That's essentially what's happening here, except instead of water, it's star stuff being woven into this intricate pattern over millennia. Hubble's razor-sharp images reveal even more complexity. The nebula's central region isn't just a smooth spiral, it's a labyrinth of knots and filaments, with shockwaves rippling through the gas where fast-moving stellar winds collide with slower debris. These turbulent zones glow brightest in oxygen and hydrogen emissions, painting the nebula's spine in vivid hues. Meanwhile, infrared observations uncover a dense, dusty disk encircling the binary pair, a cosmic carousel that likely channels the outflows into those crisp, symmetrical arms. But the real intrigue lies in the timing. Spectroscopy shows the nebula's outer loops are expanding slower than the inner regions, suggesting the dying star didn't eject its material all at once but in pulses. Each outburst interacted differently with the companion star's gravity, creating nested layers of spiral structure. Some researchers even speculate the companion might have plunged through the primary star's envelope at one point, stirring the gas like a spoon in turbulent water and amplifying the spiral's twist. What makes NGC 5189 truly extraordinary is its defiance of expectations. Planetary nebulae were once thought to be relatively simple, spherical phenomena, but this twisted masterpiece proves otherwise. It's a testament to how binary stars can warp the death throes of their partners, turning stellar demise into a work of art. And as we study its coils, we're not just seeing a nebula, we're glimpsing the invisible dance of gravity itself, written across the cosmos in luminous gas. NGC 6826, known as the Blinking Planetary, plays a cosmic trick on anyone who dares to stare directly at it. Look straight at this nebula through a telescope, and it seems to vanish, a faint, ghostly wisp barely clinging to visibility. But glance slightly to the side, employing your peripheral vision, and suddenly it snaps into focus, glowing with an eerie intensity. This bizarre phenomenon isn't magic, it's a quirk of human biology. Our eyes' rod cells, which dominate peripheral vision, excel at detecting faint, diffuse light, while the cone cells at the center of our gaze struggle with such dim targets. The result, a nebula that literally winks at observers as if sharing some celestial inside joke. But the real intrigue lies beyond this optical illusion. Hubble's sharp gaze reveals NGC 6826 as a turbulent arena, where knots of gas race outward at speeds exceeding 150 kilometers per second, fast enough to cross the Atlantic Ocean in under 30 seconds. These aren't lazy drifts of stellar material, they're violent ejecta flung from the central star during its death throes. The nebula's inner shell shimmers with hundreds of these dense, fast-moving globules, each one larger than our solar system, glowing blue from ionized oxygen. Their trajectory isn't random, many align along axis-like structures, hinting at magnetic fields or binary star interactions sculpting their paths. At the heart of this kinetic display sits one of the brightest known white dwarfs, blazing with surface temperatures near 50,000 degrees Celsius. This stellar remnant doesn't just illuminate the nebula, it powers a phenomenon called photoionization, where its ultraviolet radiation strips electrons from surrounding gas atoms, making them fluoresce in vivid colors. Yet the star's brilliance creates another puzzle, a vast, faint halo surrounding the main nebula, invisible to most telescopes until recent decades. This outer shroud, stretching over 2 light years, is likely material ejected tens of thousands of years before the inner nebula formed, a fossil record of the star's earlier, quieter shedding phase. What truly sets the blinking planetary apart are those speeding knots. Spectroscopy shows they're rich in nitrogen and helium, elements cooked up in the star's core and now being flung into interstellar space. Some appear to be trailing comet-like tails, evidence of their supersonic motion through slower-moving gas. Others cluster in arc-shaped formations, suggesting shock waves from periodic stellar outbursts. Intriguingly, their expansion rate implies the nebula is shockingly young, perhaps only 5,000 years old, making it a stellar infant compared to most planetary nebulae. Yet for all its violence, NGC 6826 maintains an uncanny symmetry. Its main shell forms a near-perfect ellipse with faint flyer, fast low ionization emission regions protruding from opposite poles like tiny handles. These jet-like structures, common in so-called butterfly nebulae, add to the enigma. How can such precision emerge from such chaos? Current theories point to the central star's spin or an unseen companion star's gravitational pull, channeling the eruptions into orderly patterns. The blinking planetary isn't just a pretty illusion, it's a time capsule. By studying its knots' composition and motion, astronomers trace the final stages of sun-like stars, watching how they seed the cosmos with heavy elements. Every wink conceals a deeper truth, that even in death, stars sculpt the universe with clockwork precision and riotous energy, writing their legacies in glowing gas. NGC 7009, the Saturn Nebula, earns its name from the 2 mysterious ansi, extending from its core like celestial rings, ethereal handles of glowing gas that mirror the iconic look of its planetary namesake. But these aren't just static decorations. They're the result of a dying star's furious last act, where ionized gas races outward at speeds exceeding 100 kilometers per second, sculpted by forces we're only beginning to understand. At the nebula's heart lies a white dwarf hotter than 55,000 degrees Celsius, its ultraviolet radiation stripping electrons from surrounding gas and setting the entire structure aglow in vivid hues of blue and green. What makes the Saturn Nebula extraordinary isn't just its symmetry, it's the physics behind those ansi. Unlike Saturn's icy rings, these extensions are no gentle disks. Hubble's close-up images reveal them as high-velocity jets, funneled through space by the star's powerful magnetic fields or the gravitational tug of an unseen companion. Each answer stretches nearly half a light-year from the central star, their tips glowing brighter where they slam into slower-moving material, creating shock waves visible in X-ray observations. It's as if the star, in its death throes, fired off twin cannons of superheated plasma into the cosmos. Even more intriguing is the nebula's layered structure. The innermost shell, dense and turbulent, pulses with oxygen emissions, while the outer regions dissolve into delicate filaments laced with nitrogen. This chemical gradient tells a story of the star's evolution, each layer representing a different phase of its demise. The ansi, however, defy this orderly progression. Spectroscopy shows they're rich in helium and neon, elements typically forged deep in a star's core, suggesting they were launched through some violent, concentrated eruption rather than a steady wind. Then there's the mystery of their shape. While most bipolar nebulae exhibit smooth outflows, the Saturn Nebula's ansi are knotted and braided, with substructures resembling beads on a string. One theory proposes that the central star's rotation, amplified as it collapsed into a white dwarf, acts like a cosmic centrifuge, flinging material outward in spiraling streams. Another points to instabilities in the outflow itself, regions where gas clumps and stretches under its own turbulent motion. But perhaps the most astonishing detail is the nebula's age. At roughly 5,000 years old, it's a fleeting spectacle in cosmic terms, caught in the brief window between a star's death and the dispersal of its remnants. This youth makes it a laboratory for studying stellar feedback, how dying stars shape their own demise. The ANSI, in particular, offer clues about how planetary nebulae transition from spherical to complex forms, a process that might hinge on binary interactions or magnetic fields we've yet to fully map. The Saturn Nebula isn't just a pretty imitation of a planet. It's a dynamic, evolving system where gravity, radiation, and magnetism collide, a reminder that even in death, stars can craft structures of breathtaking precision and violence. And as we unravel its secrets, we're not just learning about one celestial object. We're decoding the universal processes that turn stellar endings into new beginnings. NGC 7662, the Blue Snowball, glows like a lone holiday ornament adrift in the cosmos, a near-perfect sphere of ionized gas so symmetrical it seems almost too precise to be natural. This planetary nebula stands out not just for its vibrant azure hue, but for the crispness of its edges, as if some cosmic hand had blown a bubble and frozen it mid-expansion. At its heart, a white dwarf burns with ultraviolet fury, its radiation exciting the surrounding gas into a fluorescent blue halo that spans roughly half a light-year. But the real magic lies in the detail's tiny, enigmatic structures called flyer, which defy the nebula's serene appearance with their chaotic energy. These flyer, short for fast low ionization emission regions, are the snowball's rebellious streaks. They appear as faint, finger-like protrusions along the nebula's polar axis, stretching outward like cosmic fireworks frozen in time. Unlike the rest of the nebula, which glows brightly from ionized oxygen and nitrogen, flyer emit light from lower energy states, suggesting they're cooler and denser than their surroundings. Yet paradoxically, they're moving faster, hurtling through space at speeds exceeding 100 kilometers per second. Their origins are a puzzle. One theory suggests they're jets of material launched by the dying star during its final throes, channeled by magnetic fields or the gravitational influence of an unseen companion. Another proposes they're shockwaves from stellar winds plowing into older, slower-moving ejecta, creating these luminous ripples in the nebula's otherwise smooth flow. Hubble's close-ups reveal even more complexity. The Blue Snowball isn't just a simple shell, it's layered, with concentric rings of gas marking periodic eruptions from the central star. These nested spheres tell a story of fits and starts, a star shedding its skin in pulses rather than a single, smooth exhale. The flyer, meanwhile, seem to pierce through these layers like needles, their paths undisturbed by the nebula's delicate infrastructure. Some even show knotty substructures, dense clumps of material that have somehow survived the star's relentless radiation. What makes this nebula particularly fascinating is its chemical fingerprint. The Blue Snowball is rich in helium and nitrogen, elements typically forged deep within a star's core and flung outward during its death. Yet spectral analysis also reveals traces of neon and argon-heavy elements that hint at the star's original mass and the nuclear processes that governed its life. This mix of materials is now being recycled into the interstellar medium, future fuel for new stars and planets. The nebula's almost mathematical symmetry raises another question: how does such precision emerge from chaos? Most planetary nebulae are messy, their shapes warped by binary companions or stellar rotation. The Blue Snowball's near-perfect sphere suggests a remarkably stable death, a star that expelled its outer layers evenly in all directions. But those flyer complicate the picture, whispering of hidden turbulence beneath the calm facade. Perhaps the most tantalizing clue lies in the flyer's alignment. They're not randomly placed, they trace the ghostly imprint of the star's rotational axis, a relic of its spin frozen in time. This hints that even in death, a star's dynamics can leave an indelible mark on its remains. The Blue Snowball, with its serene glow and secret flares, is more than a pretty cosmic bauble. It's a testament to the delicate interplay of forces that shape a star's final act, and a reminder that even in symmetry, there's always room for surprises. NGC 40, the Bow Tie Nebula, is anything but a serene cosmic spectacle. This is a star's death cry etched into space with violent elegance. At first glance, it resembles a celestial ribbon, its glowing loops of gas pinched at the center into a tight knot. But this isn't gentle origami. The nebula's distinctive shape is forged by hurricane-force winds roaring from its central star at speeds that would cross Earth's diameter in seconds. That star, a white dwarf scorching at 50,000 degrees Celsius, isn't just shining, it's screaming. Its ultraviolet radiation and particle blasts are so intense, they've sculpted the surrounding gas into this twisted, bow-tie silhouette, a cosmic collision between beauty and brutality. What makes this nebula truly bizarre is the physics behind its form. Most planetary nebulae expand smoothly, but the bow tie's waist is cinched tight, as if gripped by an invisible hand. The culprit, the central star's extreme winds, which have carved a cavity in the slower-moving gas ejected earlier in its death throes. Picture a sandblaster firing into a cloud of smoke. The faster material bores through the slower, leaving behind hollowed-out lobes connected by that narrow, glowing bridge. Spectroscopy reveals these winds are laced with carbon and oxygen, elements cooked in the star's core and now being hurled into the void. Yet the bow tie hides stranger secrets. Hubble's images show the nebula's loops aren't perfect arcs. They're studded with knots and filaments, tiny denser regions where gas clumps together like beads on a string. These knots glow brighter in nitrogen-rich emissions, suggesting they're remnants of the star's cooler outer layers, somehow surviving the radiation onslaught. Even more puzzling are the faint, jet-like structures near the nebula's poles. Unlike the smooth outflows seen in other nebulae, these jets appear fragmented, as if the star's death came in stuttering bursts rather than a single explosive exhale. The real enigma, though, is the nebula's temperature map. While the central regions blaze under the white dwarf's glare, the outer loops are curiously cooler, a thermal paradox. Some astronomers theorize magnetic fields channel the star's energy unevenly, leaving pockets of gas to chill in the cosmic shadows. Others propose the knots act like insulation, shielding surrounding material from the full fury of the radiation. Either way, the result is a nebula that defies simple categorization, its layers telling conflicting stories of heat and resilience. Then there's the matter of scale. The bow tie spans roughly half a light year, but its structure suggests it's shockingly young, perhaps only a few thousand years old. In cosmic terms, this is a newborn, still reeling from the violence of its formation. And that youth makes it a time capsule. By studying how its winds interact with the gas, astronomers glimpse the chaotic moments after a star's collapse, watching physics play out in real time. NGC 40 isn't just another pretty nebula. It's a laboratory for extreme stellar mechanics, where winds rip through space at unimaginable speeds, where gas resists annihilation in defiant clumps, and where the universe proves once again that even destruction can craft breathtaking symmetry. Every twist of its luminous bow tie whispers the same truth. In the cosmos, chaos doesn't just destroy, it creates. NGC 246, the Skull Nebula, drifts through the constellation Cetus like a phantom's remains, its hollow eye sockets glowing with an eerie blue-white radiance against the cosmic dark. This isn't just another planetary nebula, it's a celestial memento mori, a death mask carved by stellar winds and radiation. What makes this cosmic skull so chilling isn't just its appearance, it's the trio of stars lurking at its core, locked in a gravitational dance that's slowly unraveling the nebula's ghostly visage. The skull's hollow eyes are actually vast cavities, blasted open by the fierce stellar winds of the central white dwarf, one of the hottest known, with temperatures soaring past 200,000 degrees Celsius. This dying star's ultraviolet fury ionizes the surrounding gas, making it fluoresce in haunting hues of blue and green. but the real horror show twist. It's not alone. Orbiting the white dwarf are two other stars, a dim red dwarf and a more distant companion, forming a rare triple system that's warping the nebula's expansion into this macabre shape. Imagine a lantern hung between three swaying pendulums, casting shifting shadows on a smoke-filled room. That's essentially what's happening here, but on a scale spanning trillions of kilometers. Hubble's close-ups reveal the skull's finer details, filamentary structures weaving through the gas like skeletal ribs, and knots of denser material stubbornly resisting the stellar wind's onslaught. These clumps, rich in nitrogen and oxygen, glow ruby red in certain wavelengths, tracing the remnants of the progenitor star's outer layers. But the most unsettling feature is the nebula's asymmetry. Unlike the neat rings of younger planetary nebulae, the skull's shell is fractured and lopsided, its eastern side stretched thinner, likely sculpted by the gravitational tug of war between the triple stars. The white dwarf's radiation punches through THESE Chinese letter, creating the illusion of hollow eye sockets peering eternally into the void. What's even stranger is the nebula's age. Most planetary nebulae fade within tens of thousands of years, but the skull's outer halo suggests it's been expanding for over 6,000 centuries. That makes it a celestial elder, its outer wisps nearly dissolved into the interstellar medium. Yet despite its longevity, the inner regions remain dynamic. Spectroscopy shows gas racing outward at 50 kilometers per second, while the central stars continue to pump energy into the system, lighting up new filaments like a ghastly strobe. But the skull's greatest mystery lies in its chemistry. The nebula's gas is unusually rich in hydrogen, a rarity for objects surrounding white dwarfs, most of which have long since burned or blown away their lightest elements. One theory suggests the red dwarf companion might be feeding the system, shedding hydrogen through stellar winds or roch lobe overflow. Another proposes that the nebula's progenitor star was anomalously hydrogen-rich to begin with, a cosmic oddity even before its demise. Gazing at NGC 246, we're not just seeing a death rattle, we're witnessing a stellar afterlife. The interplay of radiation, gravity, and time has turned this nebula into a cosmic reliquary, where the remains of a star and the dynamics of its companions conspire to create something both beautiful and unnerving. It's a reminder that even in the cold expanse of space, the universe has a flair for the dramatic and a taste for the macabre. NGC 3132, the 8-burst nebula, spins through space like a glowing celestial pinwheel, its intricate layers of gas expanding in near-perfect concentric rings. At first glance, it resembles a cosmic bullseye, a frozen explosion frozen in time. But this nebula's precision isn't just random artistry, it's the handiwork of a stellar duo locked in a gravitational ballet, their partnership shaping one of the most symmetrical nebulae ever discovered. At its core burns an unlikely pair, a searing white dwarf, its surface hotter than 100,000 degrees Celsius, and a far cooler companion star still clinging to its yellow hue. This temperature mismatch is the key to the nebula's remarkable structure. As the white dwarf bombards its surroundings with ultraviolet radiation, its cooler sibling tugs at the ejected gas, sculpting it into those mesmerizing rings. Imagine a potter's wheel where one hand spins the clay while another gently presses patterns into its surface. That's essentially what's happening here, but on a scale spanning trillions of kilometers. Hubble's razor-sharp images reveal even more complexity. The nebula's innermost rings glow vivid blue from ionized oxygen, their edges sharp as crystal evidence of recent violent eruptions. Farther out, the rings soften into reds and oranges, where nitrogen and hydrogen emissions dominate, marking older ejecta that's had time to expand and cool. But the real marvel lies in the faint, concentric ripples beyond these main structures, delicate echoes of mass loss events that occurred tens of thousands of years before the nebula's final dramatic collapse. What makes this system truly extraordinary is the dynamic between the two stars. The white dwarf, though small, dominates the energy output, its radiation inflating a vast bubble of ionized gas. Meanwhile, the yellow companion, seemingly passive, exerts subtle gravitational nudges that corral this expanding shell into orderly rings. Spectroscopy shows these stars orbit each other every few centuries, their dance creating rhythmic density waves in the nebula's fabric. Some researchers liken it to a lighthouse beam sweeping through fog, where each rotation leaves behind a new luminous imprint, but the 8-burst nebula hides deeper puzzles. Near its poles, faint jets pierce through the rings, fast-moving streams of material that shouldn't exist in such a symmetrical system. These jets, rich in helium and neon, suggest the white dwarf experienced episodic outbursts during its death throes, brief spasms of activity that punch through the otherwise orderly outflows. Even more perplexing are the knots, dense globules of gas embedded in the rings like beads on a string. These knots somehow withstand the white dwarf's blistering radiation, their survival hinting at magnetic fields or unseen chemical processes shielding them from disintegration. The nebula's name comes from its apparent 8-lobed structure when viewed through early telescopes, an optical illusion created by overlapping rings at different angles. Modern observations, however, reveal it's fundamentally cylindrical, its symmetry so precise it's become a benchmark for studying stellar winds and ionization fronts. By analyzing how light filters through its layers, astronomers have even detected molecules like hydrogen cyanide in its cooler region's complex chemistry, thriving in what should be a sterile radiation bath. NGC 3132 isn't just a pretty cosmic target. It's a masterclass in how binary stars choreograph their final acts, transforming chaos into breathtaking order. Every ring tells a story of eruptions timed to orbital cycles, of gravity sculpting light, and of a partnership that outlasted death itself. As we unravel its secrets, we're not just studying a nebula. We're decoding the universal language of stellar transformation, written in gas and starlight. NGC 6369, the little ghost nebula, floats in the cosmos like a faint, ethereal whisper, a delicate wreath of gas so subtle early astronomers nearly missed it. Unlike the vibrant spectacle of many planetary nebulae, this one glows with a quiet luminosity, its dim blue-green rings expanding gently into space. But don't let its understated beauty fool you. This ghostly remnant is the signature of a star's violent metamorphosis, a transition from fiery giant to dense white dwarf frozen in time. What makes the little ghost so captivating is its structure. Hubble's sharp vision reveals not one but two concentric shells, an inner ring glowing fiercely in ionized oxygen and a fainter outer halo rich in nitrogen. This double-layered anatomy tells the story of the star's death in stages. The inner ring represents the star's final, furious ejections, gas hurled outward at nearly 30 kilometers per second as the dying sun convulsed. The outer halo, meanwhile, is the ghost of an earlier, shedding material expelled tens of thousands of years before the core's collapse, now illuminated by the ultraviolet glare of the newly exposed white dwarf. At the heart of this wraith-like nebula lies the star itself, a white dwarf blazing at over 50,000 degrees Celsius. Its radiation bathes the surrounding gas, stripping electrons and forcing them to fluoresce in eerie hues. Yet for all its ferocity, the star's light barely reaches us. The little ghost is faint not because it's small, but because much of its gas is spread thin, a diffuse veil that scatters starlight like fog under a distant street lamp. The real mystery, though, lies in the nebula's asymmetry. While the inner ring appears mostly spherical, it's subtly pinched at the poles, creating an hourglass silhouette hidden within the glow. Some astronomers attribute this to the star's rotation spinning rapidly as it shrank, its centrifugal force flinging material outward more vigorously along the equator. Others suspect the gravitational tug of an unseen companion, a cosmic partner warping the outflow like an invisible hand pressing into smoke. Then there's the matter of the nebula's gaps. High-resolution images show dark patches in the inner ring regions where the gas is oddly depleted. These voids might be evidence of dense, planet-like objects forming from the star's ejected material, their gravity carving holes as they orbit. Or they could be shadows cast by clumps of dust swirling within the nebula, temporary obstructions in an ever-evolving structure. The little ghost's most haunting feature, however, is its transience. At roughly 5,000 years old, it's a fleeting phenomenon by cosmic standards. Already, its outer layers are dissipating into interstellar space, their atoms destined to be recycled into future stars and planets. Yet, even as it fades, this nebula offers a rare glimpse into stellar evolution's quiet moments, not the explosive deaths of supernova, but the gentle unraveling of sun-like stars, their final breath written in glowing gas. NGC 6369 isn't just a celestial spectre. It's a reminder that even in death, stars leave behind echoes, subtle, beautiful, and rich with secrets waiting to be deciphered. NGC 2440, the cosmic caterpillar, writhes through space like a stellar lava mid-metamorphosis, its twisted, irregular lobes glowing in violent shades of blue and orange. This isn't a serene planetary nebula. It's a celestial battleground where a dying star's last convulsions have torn its expelled gases into jagged, asymmetrical shards. At the heart of this chaos lies one of the hottest white dwarfs ever discovered, a stellar ember blazing at 200,000 degrees Celsius, so searing it outshines entire galaxies in ultraviolet light. The nebula's tortured shape tells a story of rebellion. Unlike the neat rings or symmetrical jets seen in other planetary nebulae, the cosmic caterpillar's lobes erupt in opposing directions like fractured wings. Hubble's images reveal turbulent ridges and filamentary structures, evidence of explosive outbursts that occurred at different times and angles. The northern lobe stretches farther and glows fiercer, its gas ionized by the white dwarf's radiation into vivid blues. The southern lobe, meanwhile, appears stunted and knotted, rich in nitrogen that paints it rusty orange, a clue that this material was ejected earlier, then sculpted by later eruptions. This lopsided violence suggests the dying star didn't go quietly but suffered spasmodic fits, belching material in erratic bursts. Then there's the white dwarf itself, a stellar remnant so extreme it defies expectations. Spectroscopy reveals its atmosphere is laced with carbon and oxygen, the ashes of nuclear fusion, but also shockingly high concentrations of neon. This rare composition hints the star was once much heavier than our Sun, its core pressures so intense they forged exotic elements before its collapse. Now exposed to the void, this tiny powerhouse, no larger than Earth, pumps out enough ultraviolet radiation to light up the surrounding gas like a fluorescent sign. But the real enigma lies in the nebula's knots. Dense clumps of gas, some larger than our solar system, dot the lobes like beads on a broken string. These aren't passive debris, they're racing outward at speeds exceeding 150 kilometers per second, their surfaces glowing where the white dwarf's radiation slams into them. Some even trail comet-like tails, gas stripped away by the stellar wind. How these knots survive the radiation onslaught is a mystery. Magnetic fields may act like cosmic armor, or perhaps their sheer density shields their cores from evaporation. The most haunting detail, NGC 2440's youth. At roughly 4,000 years old, it's a newborn by cosmic standards, its central star still cooling from its collapse. This makes it a rare window into the instant aftermath of stellar death. A snapshot of chaos before time smooths it into something more orderly. Every twist of its lobes, every glowing knot, is a freeze frame of a star's final rebellion against the dark. The cosmic caterpillar isn't just a nebula. It's a lesson in stellar violence, a reminder that even in death, stars don't fade gently. They thrash, they erupt, and they leave behind scars of light that linger for millennia. And as we study its turbulent beauty, we're not just observing a celestial object, we're witnessing the raw, unfiltered physics of transformation itself. NGC 6781, the Owl's Eye Nebula, gazes out from the cosmic dark with an eerie, almost sentient presence, its faint eyes glowing through the thinning veil of its outer shell like spectral spotlights. This planetary nebula doesn't just resemble an owl's stare, it embodies the illusion so perfectly you'd swear the cosmos designed it to unsettle us. But those haunting eyes aren't the work of some celestial artist. They're windows carved by physics where the central star's relentless radiation has punched through weaker regions of the nebula's gas, creating voids that let starlight stream into space. The effect is uncanny, two brighter patches, symmetrical and watchful, peering through the nebula's shroud like a predator in the night. What makes this structure even more fascinating is the balance of forces behind it. The owl's eye isn't just a static mask, it's a dynamic battlefield where radiation and gas wage war. The central white dwarf, hotter than 60,000 degrees Celsius, bombards its surroundings with ultraviolet fury, ionizing the nebula's hydrogen and oxygen into glowing blues and greens. But the shell isn't uniform. Some areas, denser and more resistant, absorb and scatter this light, while thinner zones, those eerie eyes, allow it to pass almost unimpeded. Hubble's sharp vision reveals these regions aren't random gaps. They align along the star's rotational axis, hinting that the dying star's spin or magnetic fields funneled its final eruptions into bipolar outflows, leaving the poles more vulnerable to erosion over time. Then there's the halo, a vast, faint envelope stretching far beyond the iconic eyes, barely visible except to the most sensitive telescopes. This outer shroud is the ghost of the star's earlier, quieter death throes, material shed tens of thousands of years before the inner nebula formed. Its asymmetry whispers of past disturbances, perhaps a companion star's gravitational nudge or interstellar winds sculpting the outflow into this haunting silhouette. But the real mystery lies in the eye's chemistry. Spectroscopy shows they're rich in doubly ionized oxygen, a signature of extreme ultraviolet exposure. Yet surrounding these bright patches are intricate tendrils of cooler gas, knots and braids that somehow withstand the radiation onslaught. Some astronomers speculate magnetic fields preserve these structures, acting like cosmic scaffolding. Others propose the knots are dense enough to self-shield, their outer layers evaporating while their cores remain intact. Either way, their persistence adds texture to the owl's gaze, like wrinkles in an ancient, knowing stare. The owl's eye isn't just a cosmic curiosity, it's a lesson in stellar mortality. By studying how light escapes its shell, astronomers decode the mechanics of mass loss, the way dying stars shed their skins unevenly, leaving behind clues to their turbulent lives. Every flicker in those watchful eyes carries a story of nuclear fires gone dark, of gravity's inexorable pull, and of the beautiful, unsettling symmetries that emerge when chaos meets time. NGC 6751, the glowing eye nebula, peers through the cosmic void like an unblinking sentinel, its intricate, swirling filaments illuminated by the searing gaze of its central star. This isn't just another planetary nebula. It's a masterpiece of stellar death, where gas expelled from a dying sun has been sculpted into delicate tendrils that stretch over 2.5 light years. Hubble's razor-sharp images reveal these filaments in astonishing detail, braided, knotted, and intertwined like threads in a celestial tapestry, each one glowing under the relentless ultraviolet assault of the white dwarf at the nebula's heart. What makes this cosmic eye so mesmerizing is the sheer violence behind its beauty. The central star, a white dwarf hotter than 140,000 degrees Celsius, bombards the surrounding gas with enough radiation to strip electrons from atoms, forcing them to fluoresce in vivid blues and greens. The nebula's intricate structure isn't random, it's a fossil record of the star's death throes, where successive waves of ejected material collided and tangled, frozen in time. Some filaments race outward at speeds exceeding 40 kilometers per second, their paths warped by shock waves and magnetic fields, while others curl inward like smoke caught in an invisible eddy. Yet the real enigma lies in the nebula's asymmetry. Unlike the perfect rings of younger planetary nebulae, the glowing eye is lopsided, with its northern hemisphere brighter and more extended than the southern. This imbalance hints at a turbulent past. Perhaps the star's rotation flung material unevenly into space, or a companion star's gravitational pull tugged the outflow into this twisted silhouette. Spectroscopic studies reveal even more intrigue. The nebula's gas is laced with heavy elements like neon and argon, forged in the star's core and now being scattered into the interstellar medium. But the most haunting feature is the central star itself. Nearly invisible in optical light, it dominates in ultraviolet, its radiation so intense it carves voids in the surrounding gas, creating the illusion of a dark pupil at the center of the glowing iris. This star isn't just hot, it's dying violently. Observations suggest it's pulsating, its brightness flickering as it cools, its final energy bleeding into the nebula like a fading heartbeat. The glowing eye isn't just a spectacle, it's a time capsule. Every filament, every knot holds clues to how stars recycle their elements into the cosmos. And as we study its radiant gaze, we're reminded that even in death, stars leave behind more than light. They leave behind mysteries waiting to be unraveled. NGC 3918, the southern planetary, gleams in the constellation Centaurus like a celestial jewel, its vibrant blue core encased in a delicate, elongated shell that stretches across the void. This isn't just another pretty nebula, it's a textbook example of extreme stellar mechanics in action. What makes it so mesmerizing isn't just its color, though the sapphire glow of doubly ionized oxygen is breathtaking, but the illusion it creates. From our vantage point, the nebula appears as two distinct shells, one nested inside the other like a cosmic matryoshka doll. But this double shell effect isn't real. It's a trick of perspective, a visual sleight of hand caused by the nebula's bipolar outflows, twin jets of gas screaming outward at hundreds of kilometers per second, pinched at the waist into an hourglass silhouette by forces we're still unraveling. At the heart of this spectacle lies one of the fastest evolving stars known to science. The central white dwarf, hotter than 70,000 degrees Celsius, isn't just shining, it's hemorrhaging material at an astonishing rate. Spectroscopic studies reveal its stellar wind tears through space at over 2,000 kilometers per second, a supersonic gale so fierce it's sculpting the surrounding gas into those iconic lobes. Yet the real marvel is the nebula's waist, that narrow, glowing bridge connecting the two hemispheres. Hubble's close-ups show it's not a smooth bottleneck but a turbulent zone, riddled with shockwaves where fast-moving jets collide with slower, older ejecta. The violence here is so extreme, it heats the gas to millions of degrees, making it visible in X-rays, a rare trait for planetary nebulae. Then there's the matter of scale. While the inner shell spans roughly 1/5 of a light year, the outer halo stretches 3 times farther, evidence of the star's earlier, mass loss episodes. This layered structure acts like a cosmic timeline. The outer halo, rich in nitrogen, represents material shed when the star was still a red giant, puffing away its outer layers gently. The inner shell, ablaze with oxygen and neon, marks the star's violent final act when its exposed core began blasting radiation like a runaway furnace. But the southern planetary's greatest mystery is its symmetry. Unlike the chaotic twists of younger nebulae, NGC 3918's lobes are remarkably balanced, a puzzle given the star's extreme mass loss. One theory suggests a binary companion's gravitational pull keeps the outflows aligned, like an invisible rudder steering the chaos. Another points to the star's magnetic fields, which may channel the winds into collimated jets. Supporting this idea are faint, knotty structures along the lobe's edges, clumps of denser gas that seem to trace magnetic field lines, frozen in place like iron filings around a magnet. Perhaps the most startling revelation comes from the central star itself. Observations show its temperature fluctuates unpredictably, its brightness flickering as if struggling to stabilize. Some astronomers speculate this could be due to residual nuclear burning on its surface, a last-ditch fusion of leftover helium, or interactions with an unseen companion star. Whatever the cause, the star's instability adds another layer of drama to an already dynamic system, proving that even in death, stars refuse to go quietly. The southern planetary isn't just a showpiece of the southern skies. It's a living laboratory where the physics of stellar demise plays out in real time. Every glowing filament, every shock-heated knot, tells a story of winds that shape galaxies, of elements forged in stellar cores, and of the beautiful, violent symmetry that emerges when a star breathes its last. And as we study its intricacies, we're reminded that the universe's most dazzling art often arises from its most destructive forces. NGC 6572, the Emerald Nebula, blazes in the night sky like a stolen piece of a distant galaxy's treasure, its luminous green glow so intense it almost seems unnatural. This isn't the soft pastel of most planetary nebulae. It's a radiant, almost electric green, the kind of hue you'd expect from a sci-fi alien world, not the remnants of a dying star. The secret behind this dazzling color, ionized oxygen, superheated to temperatures that force it to emit light at a very specific wavelength of 5,000 angstroms, a shade of green so pure it's become a benchmark for astronomers studying gas composition across the cosmos. What makes the Emerald Nebula truly extraordinary is its density. While most planetary nebulae sprawl across light years, NGC 6572 is compact, barely a few arcseconds wide in telescopic views. Don't let its small size fool you, though. Packed into that tiny volume is a maelstrom of gas so dense it rivals the atmospheres of some planets. Every cubic centimeter holds thousands of atoms, a far cry from the near-perfect vacuum of typical interstellar space. This density amplifies the nebula's glow, concentrating the light into a jewel-like point that stands out even against the star-rich backdrop of its home constellation, Ophiuchus. At its heart lies a white dwarf star, one of the hottest ever recorded, with surface temperatures soaring beyond 200,000 degrees Celsius. The star's ultraviolet radiation doesn't just illuminate the surrounding gas, it brutalizes it, stripping electrons from oxygen atoms with such force they emit that signature green light as they struggle to recombine. But the real surprise is the nebula's asymmetry. Unlike the smooth shells of younger nebulae, the Emerald's gas churns in turbulent knots and braids, visible only through high-resolution imaging. Some researchers believe this chaos stems from the dying star's magnetic fields, twisting the outflow into intricate shapes like invisible hands molding molten glass. Then there's the matter of its youth. Estimated to be less than 3,000 years old, the Emerald Nebula is practically a newborn in cosmic terms, still reeling from the violence of its formation. Spectroscopy reveals gas racing outward at speeds over 40 kilometers per second, a testament to the ferocity of the star's final eruptions. Yet despite this turbulence, the nebula's outer edges remain sharply defined, evidence of a sudden, catastrophic ejection rather than a slow, steady wind. The Emerald Nebula isn't just a pretty sight. It's a time capsule capturing the moment a star's death throws transition from chaos to structure. And as we study its vivid glow, we're not just observing a celestial object, we're witnessing the universe's ability to turn destruction into something breathtakingly beautiful, one ionized atom at a time. NGC 7293, the Helix Nebula, stares back at us like a celestial eye, its eerie blue-green glow spanning an astonishing 2.5 light-years, so vast it could swallow our entire solar system with room to spare. This isn't just the closest planetary nebula to Earth. It's one of the most structurally complex, a labyrinth of gas and dust that reveals new mysteries with every observation. The nickname Eye of God isn't just poetic gaze at Hubble's images, and you'll see the uncanny resemblance. A radiant iris of ionized oxygen, a dark pupil-like central region where the white dwarf lurks, and delicate concentric rings swirling outward like cosmic fingerprints. What makes the helix truly mesmerizing are the thousands of cometary knots speckling its outer halo, dense, teardrop-shaped globules of gas, each one larger than our solar system. These aren't static debris, they're survivors. Despite the central star's ultraviolet fury, which strips electrons from atoms and heats gas to tens of thousands of degrees, these knots stubbornly hold their form. Their secret, sheer density. Each knot packs enough mass to shield its core from the radiation storm, with cooler molecular hydrogen and even dust grains hiding inside materials that should have been obliterated in such a hostile environment. Some even sport glowing tails, streaming behind them like cosmic kites caught in a stellar wind, as they're slowly evaporated by the white dwarf's relentless glare. The nebula's spine-tingling symmetry hides violent origins. At its heart lies a white dwarf hotter than 60,000 degrees Celsius, the exposed core of a star that once resembled our Sun. When it exhausted its nuclear fuel, it didn't just shed its outer layers, it convulsed, ejecting gas in pulses over millennia. The result, those haunting concentric rings, each one a fossilized shockwave from a past eruption, now illuminated like ripples in a pond under blacklight. But here's the twist, the helix isn't a perfect sphere. High-resolution spectroscopy reveals its structure is slightly flattened, likely sculpted by the dying star's rotation or the gravitational tug of an unseen companion. Then there's the mystery of the outer halo. Far beyond the iconic eye, faint filamentary loops stretch into space, remnants of material ejected tens of thousands of years before the star's final collapse. Infrared telescopes have detected complex organic molecules in these regions, polycyclic aromatic hydrocarbons, the same compounds found in soot and interstellar clouds. Their presence here defies expectations. How do these delicate carbon structures endure the central star's radiation? One theory suggests they're constantly reforming, their components shattered and reassembled in a never-ending chemical dance. But perhaps the most astonishing detail is the helix's youth. At just 10,000 years old, it's a planetary nebula in its infancy, offering astronomers a front-row seat to the early stages of stellar death. Every knot, every ripple in its gas is a freeze frame of physics in action, magnetic fields threading through ionized plasma, shockwaves heating gas to X-ray temperatures, and the raw elements of future stars being sown into the void. Gazing into the Helix Nebula isn't just observing a cosmic object. It's witnessing the fate that awaits our own Sun, a reminder that even the most familiar stars will one day unravel into something both beautiful and terrifying, their final breaths etching stories across the sky that will linger long after they're gone. NGC 3587, the Owl Nebula, gazes silently from the depths of space like an ancient sentinel, its eerie, dark eyes peering through the glowing veil of expelled stellar material. These shadowy voids aren't random gaps in the gas. They're cosmic illusions, regions where denser knots of material have gathered to block the intense ultraviolet radiation pouring from the nebula's central star. The effect is haunting, two symmetrical patches of darkness set against a luminous blue-green backdrop, mimicking the watchful stare of its namesake. But this celestial owl isn't just a trick of perspective. Those dark eyes are dynamic structures, sculpted by the delicate interplay between radiation and gravity, where pockets of slightly denser gas resist erosion while thinner regions around them glow fiercely under the star's relentless glare. Hubble's sharp vision reveals even more complexity within those shadowed voids. The material forming the owl's pupils isn't uniform filamentary tendrils weaved through the darkness. evidence of turbulent motions where fast-moving stellar winds collide with slower ejecta. These knots are rich in molecular hydrogen and dust, remnants of the star's cooler outer layers that somehow survived the violent transition to a white dwarf. Their persistence is a puzzle. Theory suggests magnetic fields may be reinforcing these dense regions, acting like cosmic scaffolding to shield them from evaporation. Alternatively, their sheer mass might provide enough gravitational stability to withstand the radiation onslaught, at least temporarily. Beyond the iconic eyes, the Owl Nebula reveals another layer of intrigue, a vast, diaphanous outer halo stretching nearly 3 light-years across. This ethereal shroud is only visible through long-exposure imaging, a whisper-thin remnant of the star's earlier, mass loss episodes. Unlike the bright inner shell, which glows from ionized oxygen and nitrogen, the halo emits faint red hues, a signature of hydrogen atoms recombining at the fringes of the nebula's influence. Its asymmetry tells a story of past disturbances. Some sections appear stretched and warped, possibly shaped by interstellar winds or the gravitational nudges of nearby stars as the nebula drifts through its galactic neighborhood. At the heart of this ghostly structure lies the nebula's engine, a white dwarf star burning at nearly 70,000 degrees Celsius. Unlike younger planetary nebulae where the central star dominates the view, this one hides in plain sight, its light heavily absorbed by the surrounding gas. Infrared observations, however, pierce through the veil, revealing a stellar remnant flickering with variability. Some astronomers speculate this flickering stems from residual nuclear burning on its surface, helium shells igniting in sporadic fusion events, while others suggest the influence of a binary companion, its gravitational tug stirring the dying embers of the star into erratic brilliance. What makes the Owl Nebula truly remarkable is its age. Estimated at 12,000 years old, it's a middle-aged planetary nebula, far enough along in its evolution for the inner shells to have expanded and thinned, yet young enough that its outer halo hasn't fully dissipated into the interstellar medium. This transitional phase offers a rare opportunity to study how these structures decay over time. The dark eyes, for instance, won't last forever. Simulations show they'll gradually erode as the white dwarf's radiation eats away at their edges, transforming the owl's gaze into a hollow stare before vanishing entirely. The Owl Nebula isn't just a celestial curiosity, it's a cosmic clock, its layers marking the passage of time since the star's demise. Every shadowed knot, every faint ripple in its halo holds clues to the physics of stellar afterlife, how gas interacts with radiation, how asymmetry emerges from spherical beginnings, and how the universe recycles the ashes of dead stars into the raw materials of new beginnings. And as we unravel its secrets, we're reminded that even in the depths of space, nature crafts art with the precision of a master sculptor, one ionized atom at a time. NGC 1501, the Oyster Nebula, isn't just a static shell of gas. It's a cosmic metronome, pulsing with rhythmic brilliance as its central star flickers like a lighthouse in the void. This planetary nebula, nestled in the constellation Camelopardalis, defies the serene symmetry of many of its peers. Instead of smooth, even rings, its structure is a chaotic tapestry of clumps and filaments, glowing in eerie greens and blues as if lit from within by some unseen fire. But the real spectacle isn't the nebula itself, it's the star at its heart, a white dwarf that refuses to fade quietly into the cosmic night. This isn't your typical stellar remnant. Most white dwarfs cool steadily, their light dimming as they drift toward oblivion. But the core of NGC 1501 is a variable star, its brightness oscillating unpredictably by up to 20% over just half an hour. These rapid fluctuations aren't just a curiosity, they're a window into the star's violent interior. Astronomers believe the pulsations stem from waves of energy rippling through the star's outer layers like seismic tremors on a planetary scale. As the star contracts and expands, its temperature soars and plummets, casting shifting illumination across the surrounding nebula like a disco ball in slow motion. The nebula's clumpy, irregular structure tells another story. Hubble's images reveal dense knots of gas strewn throughout the glowing shell, some as large as our solar system. These aren't random debris, they're survivors, pockets of material dense enough to resist the star's scorching ultraviolet winds. Spectroscopy shows they're rich in nitrogen and oxygen, elements forged in the star's core and now being blasted into space. Yet their distribution is anything but uniform. Some regions bristle with filamentary tendrils, while others appear almost hollow, as if the star's outbursts carved caverns into the nebula's flesh. What makes this system truly bizarre is the disconnect between the star's pulsations and the nebula's response. Unlike a lamp lighting a room, the nebula's glow doesn't sync perfectly with the star's flickering. There's a lag, a delay caused by the finite speed of light and the sheer scale of the structure. Gas closer to the star reacts almost instantly, brightening and dimming in near unison. But farther out, the changes arrive later, creating a ripple effect that makes the entire nebula seem to breathe. Then there's the mystery of the nebula's asymmetry. Most planetary nebulae start spherical, only to be sculpted into complex shapes by binary companions or magnetic fields. The Oyster, however, was never symmetrical to begin with. Its initial eruptions were lopsided, suggesting the dying star itself was unstable, ejecting material in fits and starts along uneven axes. Some researchers speculate the star's rapid rotation, spun up by interactions with a now-vanished companion, flung gas outward in these chaotic bursts. Others point to magnetic fields twisted into knots during the star's collapse, channeling the outflows into these jagged formations. The Oyster Nebula isn't just a relic of stellar death, it's a living laboratory. Every pulsation of its central star, every clump in its fractured shell, offers clues to the turbulent processes that govern a sun's final act. And as we watch its light dance across the centuries, we're reminded that even in the coldest depths of space, stars don't just fade, they shudder, they flare, and they leave behind echoes of their struggle written in glowing gas. NGC 2022, the red planetary, burns in the constellation Orion like a lone ember adrift in the cosmic dark, its deep crimson glow defying the usual blue-green palette of most planetary nebulae. This rare ruby hue comes from an unusual abundance of ionized nitrogen, a chemical signature revealing the violent history of its central star. While oxygen typically dominates these stellar remnants, painting them in cool blues, this nebula's nitrogen-rich gas fluoresces in warm reds, as if the dying star set its own funeral shroud ablaze. What makes this nebula truly mesmerizing is its near-perfect spherical symmetry, a rarity among planetary nebulae, which often twist into hourglasses or spirals under the influence of binary companions or magnetic fields. Here, the gas expands in an almost flawless bubble, suggesting the star shed its outer layers in a remarkably even, controlled ejection. Hubble's sharp gaze reveals subtle ripples in the shell density waves frozen in time, each one marking a pulse of mass loss during the star's final millennia. These concentric rings, faint but detectable, act like tree rings for stellar death, chronicling the star's decline in gaseous strata. At the nebula's heart lies a white dwarf hotter than 80,000 degrees Celsius, its ultraviolet radiation so intense it strips electrons not just from nitrogen but from heavier elements like sulfur and neon. Spectroscopic studies reveal a shocking detail. The central star's atmosphere is laced with traces of carbon and oxygen, but nearly devoid of hydrogen, evidence it burned through its lightest elements long before collapse, leaving behind a smoldering core of nuclear ash. This chemical fingerprint suggests the star was once far more massive than our Sun, its core pressures so extreme they forged exotic isotopes before its dramatic unraveling. The nebula's structure holds another puzzle. While the outer shell glows uniformly in nitrogen's red light, the innermost regions shimmer with fainter blue emissions from doubly ionized oxygen. This layered chemistry implies the star's death wasn't a single event but a series of eruptions, with later outbursts plowing through earlier ejecta like shockwaves in water. The oxygen-rich material expelled in the star's last gasps now races outward at 40 kilometers per second, colliding with the slower-moving nitrogen envelope and creating delicate filamentary structures at the boundary. Perhaps the most haunting feature is the nebula's silence. Unlike younger, turbulent planetary nebulae crackling with shock-heated gas, the red planetary's expansion is eerily smooth, its symmetry barely disturbed by interstellar winds or gravitational perturbations. This tranquility hints at an isolated demise, a star dying alone in a sparse region of space, its final breaths expanding undisturbed for millennia. NGC 2022 isn't just a cosmic oddity. It's a testament to the diversity of stellar endings, proof that even in death, stars can paint the void in unexpected colors, their chemistry and symmetry telling stories of nuclear fires, violent ejections, and the quiet that follows when the flames finally flicker out. NGC 1535, the Cleopatra's Eye Nebula, gleams in the constellation Eridanus like a celestial jewel, its hypnotic layers of gas unfurling in radiant blues and greens, each ripple a frozen echo of the star's violent final act. This isn't just another planetary nebula, it's a masterclass in stellar mechanics where radiation and stellar winds wage a cosmic tug of war, sculpting gas into shapes so intricate they resemble the layered patterns of an ancient cameo. What sets this cosmic eye apart is the stark contrast between its crisp, elliptical outer shell and the turbulent chaos lurking within. Hubble's razor-sharp images reveal a central cavity where the white dwarf's relentless winds have carved a void, while the surrounding gas billows outward in delicate filaments, like smoke caught in a snapshot of explosive motion. At the heart of this spectacle lies a white dwarf hotter than 50,000 degrees Celsius, a stellar ember pouring ultraviolet radiation into its surroundings with enough ferocity to strip atoms bare. But the real drama unfolds in the nebula's layered structure. The outer shell, glowing predominantly in oxygen emissions, expands at a gentle 20 kilometers per second, its smooth contours betraying the star's initial, more orderly mass loss. In stark contrast, the inner regions churn with knots and braids, where later eruptions propelled by winds 10 times faster collide with older ejecta, superheating gas into shockwaves visible in X-ray observations. This duality makes Cleopatra's Eye a time capsule, its nested shells chronicling the star's transition from a steady red giant to a convulsing, unstable progenitor of a white dwarf. The nebula's namesake, eye illusion, isn't just poetic license. Near the core, a dark, pupil-like spot appears where the white dwarf's radiation has tunneled through thinner gas, creating a window into the nebula's depths. Surrounding it, concentric rings ripple outward, not perfect circles, but slightly flattened ellipses, hinting at the dying star's rotation or the gravitational nudge of an unseen companion. Spectroscopy reveals even more nuance. The nebula's northern hemisphere is marginally richer in nitrogen, suggesting asymmetrical mass loss, while the southern regions glow brighter in oxygen, their gas more thoroughly ionized by the star's radiation. But the true enigma lies in the filamentary structures lacing the inner shell. These aren't random wisps, they're density waves, regions where gas has clumped under its own gravity or been compressed by magnetic fields. Some stretch radially like spokes, tracing the paths of high-velocity jets from the central star. Others twist into helical patterns, as if the dying star's spin imprinted itself onto the outflow. The most striking are the so-called flyer, fast low-ionization emission regions, dense, fast-moving knots along the polar axes, their composition skewed toward nitrogen and helium, elements forged deep in the star's core. These flyer race outward at nearly 100 kilometers per second, their survival defying expectations, how do they endure the white dwarf's scorching radiation? One theory suggests magnetic fields cocoon their cores, shielding them like cosmic umbrellas. Cleopatra's Eye isn't just a static monument to stellar death, it's a dynamic laboratory. Recent observations detect subtle brightness variations in the central star, flickers that may betray residual nuclear burning on its surface or the gravitational whispers of a binary partner. Meanwhile, the nebula's outer halo, barely visible in optical light, stretches twice as far as the main shell, a relic of the star's quieter, earlier shedding phases, now illuminated by delayed fluorescence from the white dwarf's ultraviolet onslaught. What makes this nebula extraordinary isn't just its beauty, it's the physics etched into every layer. From the flyer's defiance to the precise gradients of its chemical makeup, NGC 1535 is a testament to the universe's ability to weave chaos into symmetry. And as we study its luminous gaze, we're reminded that even in destruction, stars leave behind puzzles so exquisite they demand our awe. NGC 1360, the Robin's Egg Nebula, floats in the cosmic expanse like a delicate watercolor, its soft blue-green glow so faint it nearly dissolves into the darkness of space. Unlike the sharp, concentrated shells of most planetary nebulae, this one sprawls across nearly 6 light-years, making it one of the largest known. Its name isn't just poetic. The nebula's ethereal hue and diffuse edges genuinely resemble a celestial eggshell cracked open and left to drift in the void. But don't mistake its gentle appearance for simplicity. This nebula's enormity and subtlety hide a dramatic story of stellar death unfolding at an almost leisurely pace. What makes the Robin's Egg so unusual is its expansion rate. While many planetary nebulae race outward at dozens of kilometers per second, this one's gases drift at a mere 10, barely a cosmic stroll. This slow, steady unfurling suggests the central star didn't erupt in violent spasms but shed its layers gradually, like a tree relinquishing its leaves over centuries. The result is a nebula so thinly spread that its light is easily drowned out by brighter celestial neighbors, requiring long exposure photography to reveal its full, sprawling grandeur. At its heart lies a white dwarf unlike most, cooler, older, and remarkably serene. With a surface temperature around 50,000 degrees Celsius, it's far tamer than the searing cores of younger nebulae, and its radiation lacks the punch to ionize the entire nebula uniformly. Instead, the Robin's Egg glows in patchy, uneven regions, with vast swaths of gas too faint to detect unless viewed through specialized filters. This inconsistency creates a mottled effect, as if the nebula itself is fading in and out of existence. The real intrigue lies in the nebula's structure. Most planetary nebulae form distinct shells or bipolar jets, but the Robin's Egg is almost entirely devoid of sharp edges. Instead, its outer layers blend seamlessly into the interstellar medium, like ink dispersing in water. Some researchers theorize this blurring stems from its age. At roughly 45,000 years old, it's one of the oldest known planetary nebulae, its once crisp boundaries eroded by eons of interaction with interstellar winds. Others suggest the central star's gentle mass loss never generated the shockwaves needed to carve defined features, leaving the gas to expand passively. Yet the nebula's diffuse nature doesn't mean it's devoid of complexity. Deep within its haze, astronomers have detected faint, filamentary structures, ribbons of slightly denser gas threading through the glow like ghostly veins. These filaments, visible only through advanced imaging, may be remnants of the star's magnetic field, frozen in the ejected material like cosmic fingerprints. Even more puzzling are the subtle chemical variations across the nebula. While most of its gas is hydrogen and helium, certain regions show elevated oxygen and nitrogen levels, hinting at uneven mixing during the star's death throes. The Robin's Egg Nebula challenges our assumptions about stellar endings. It's proof that not all stars die in fiery explosions or sculpted outbursts. Some fade with quiet dignity, their remnants dissipating into the cosmos with a whisper rather than a roar. And as we study its delicate glow, we're reminded that beauty in the universe isn't always bold and bright. Sometimes it lingers in the faintest light, waiting patiently to be seen. NGC 6210, the Turtle Nebula, crawls through the cosmos with an almost deliberate grace, its nested shells of gas expanding like the growth rings of an ancient tree, each layer whispering secrets of the star's violent past. This isn't just another planetary nebula, it's a time lapse of stellar demise where concentric waves of ejected material freeze-frame the star's death throes across millennia. Hubble's razor-sharp vision reveals at least 4 distinct shells, each glowing in different hues, ionized oxygen painting the innermost layers electric blue, while nitrogen-rich outer regions burn ruby red. The effect is hypnotic, a celestial Russian doll where every layer peels back to expose a new chapter in the star's unraveling. At the heart of this labyrinth lies one of the most energetic white dwarfs known, its surface scorching at 70,000 degrees Celsius. But what truly sets this star apart are the twin jets screaming from its poles at speeds approaching 150 kilometers per second, blistering torrents of gas carving through the nebula's delicate shells like cosmic blowtorches. These aren't gentle streams, they're supersonic spears stretching over half a light year and glowing fiercely in hydrogen alpha light. Their paths twist slightly, as if buffeted by unseen forces, leaving behind shock-heated wakes that ripple through the surrounding gas. Some researchers believe the star's rapid rotation or the gravitational tug of a hidden companion whips these jets into their helical dance, sculpting the nebula's intricate asymmetry. The turtle's nested shells tell another tale. Unlike the smooth, uniform expansions seen in younger nebulae, these layers are fragmented, rippled with dense knots and filamentary structures that defy erosion. Infrared observations reveal these clumps are rich in crystalline silicates, dust grains that typically form in the cool atmospheres of red giants. Their survival here, in the blistering radiation of a white dwarf, suggests they're shielded by magnetic fields or sheer density, like boulders resisting a hurricane. Even more puzzling are the shell-to-shell chemical variations. The innermost layer blazes with neon emissions, a signature of material forged in the star's final, frenzied fusion episodes. Farther out, sulfur and argon dominate, relics of earlier, shedding phases. It's as if the nebula preserves a periodic table of the star's life, each element a marker of its evolution. Then there's the matter of scale. While the inner shells span mere fractions of a light year, the outermost halo extends nearly 3 times farther, a diaphanous veil of gas so faint it was only detected by the most sensitive telescopes. This ghostly shroud likely represents the star's first, tentative steps toward demise, material ejected tens of thousands of years before the dramatic collapse that formed the visible nebula. Its presence hints at a death that wasn't sudden, but a slow unraveling punctuated by episodic outbursts. What makes the Turtle Nebula extraordinary isn't just its beauty, it's the violent harmony of its contradictions. Here, delicate shells withstand supersonic jets, crystalline dust survives stellar infernos, and a dying star's final act becomes a cosmic archive, its layers whispering stories of fusion, fury, and the fleeting nature of even the mightiest suns. NGC 4361, the cosmic jellyfish, drifts through the constellation Corvus like a phantom of the deep sea, its ethereal tentacles of gas stretching silently across the void. This planetary nebula doesn't blaze with the vivid hues of younger stellar remnants. Its glow is subtle, almost spectral, as if the dying star at its core exhaled its final breath with a whisper rather than a roar. What catches the eye are those faint, filamentary extensions, delicate strands of ionized gas curling outward like bioluminescent tendrils, each one a fossilized ripple of the star's violent transition from red giant to white dwarf. At the nebula's heart lies a central star shrouded in mystery, Unlike the searing hot white dwarfs typical of planetary nebulae, this one burns at a comparatively cool 30,000 degrees Celsius, a temperature that leaves its expelled gas dimmer and more diffused. The jellyfish's tentacles, visible only through long exposure imaging, trace the paths of ancient stellar winds, where material ejected at different velocities collided and twisted into these haunting shapes. Some filaments stretch over a light year, their ends frayed and wispy, as if dissolving into the interstellar medium. Others knot into clumps dense enough to resist the star's radiation pressure, glowing faintly in hydrogen alpha light like embers in cosmic fog. The nebula's location in Corvus, the Crow, adds another layer of intrigue. Nestled far from the Milky Way's star-rich plain, NGC 4361 floats in relative isolation, its faint glow uncontaminated by the glare of nearby stars. This solitude makes it a pristine laboratory for studying the late stages of stellar evolution. Spectroscopic analysis reveals a chemical paradox. While the inner regions shimmer with oxygen and nitrogen, the outer tentacles are disproportionately rich in sulfur, an element typically forged deeper in a star's core. One theory suggests the dying star underwent episodic eruptions, with later outbursts dredging up heavier elements and flinging them farther into space. But the real enigma is the tentacles' asymmetry. Unlike the orderly jets of younger nebulae, these filaments spiral chaotically, some even looping back toward the central star. High-resolution radio maps hint at magnetic fields warping the outflow, their invisible lines of force sculpting the gas into these organic shapes. Alternatively, the gravitational tug of an unseen companion, or even a rogue interstellar cloud passing too close, could have disrupted the nebula's expansion, leaving behind this tangled legacy. What makes the cosmic jellyfish extraordinary isn't just its appearance, it's the quiet defiance of its existence. Most planetary nebulae blaze brilliantly for just tens of thousands of years before fading. NGC 4361, by contrast, has lingered for over 100,000, its slow fade offering a rare glimpse into the final act of a star's afterlife. Those ghostly tentacles aren't just debris, they're the last echoes of a sun's voice, carrying secrets of how stars return their borrowed atoms to the universe, one faint, glowing ripple at a time. NGC 5307, the pinwheel planetary, spins through space with a hypnotic precision, its delicate spiral arms unfurling like the grooves of a cosmic vinyl record. Unlike most planetary nebulae, which form chaotic shells or ragged halos, this one displays an almost mathematically perfect spiral pattern, a structure so precise it looks engineered. The secret behind this celestial clockwork, a binary star system locked in a gravitational waltz where one star's death throes have been sculpted by the rhythmic pull of its companion. At the nebula's heart, two stars orbit each other in a tight embrace: a white dwarf, the smoldering remnant of a sun-like star, and a smaller companion whose gravity tugs at the expelled gas like an invisible hand stirring smoke. As the dying star shed its outer layers, the companion's orbit didn't just shape the outflow, it set it spinning. Picture a garden sprinkler twirling in slow motion, each rotation imprinting a new curve in the nebula's structure. But here's the twist: the system's jets aren't static. They precess, wobbling like a top as they're influenced by the binary pair's dance, carving those ethereal spiral arms into the gas over millennia. Hubble's sharp gaze reveals the spiral's astonishing detail. Each arm is a fossilized snapshot of the star's mass loss, with brighter regions marking denser ejections and darker gaps tracing quieter periods. Spectroscopy shows the arms aren't just pretty patterns, they're chemical timekeepers. The inner coils glow fiercely in ionized oxygen, evidence of the star's final, violent eruptions, while the outer turns are richer in nitrogen, relics of earlier comma shedding. This gradient isn't just artistic, it's a diary of the star's collapse written in luminous gas. The real marvel is the jet dynamics. Most planetary nebulae with bipolar outflows exhibit straight, collimated jets. NGC 5307s, however, curve gracefully, their paths bending as the binary system's gravity torques their direction. Radio observations have even detected faint shock fronts along the spiral's regions where faster-moving material plows into slower ejecta, heating gas to X-ray temperatures. These shocks aren't random, they align with the predicted precession cycle, offering rare observational proof of how binary stars choreograph their partners' deaths. Yet the pinwheel hides deeper mysteries. Infrared imaging reveals dust lanes woven into the spiral arms, cold, gritty material that shouldn't survive so close to the white dwarf's blistering radiation. One theory suggests magnetic fields trap this dust in dense filaments, shielding it like cosmic armor. Another proposes the companion star's gravity funnels dust into these discrete bands, creating the nebula's textured appearance. Either way, these dust lanes add a tactile richness to the nebula, transforming it from a mere glow into a three-dimensional sculpture. What makes NGC 5307 extraordinary isn't just its beauty, it's the physics etched into every coil. Here, the universe demonstrates how orbital mechanics can imprint order onto chaos, turning a star's death into a celestial fingerprint. And as we trace its spirals, we're not just seeing a nebula, we're witnessing the invisible hand of gravity itself, writing its laws in light. NGC 6578, the Blue Flash Nebula, doesn't just shimmer. It practically crackles with energy, its gases racing outward so fast they seem to defy the very concept of cosmic time. This isn't a slow, serene unraveling like many planetary nebulae. It's a stellar explosion frozen mid-burst, its brilliant blue-green shell expanding at a blistering 40 kilometers per second. To put that into perspective, that's fast enough to cross the distance from Earth to the Moon in less than 3 hours, a velocity so extreme it leaves shockwaves rippling through the surrounding interstellar medium like sonic booms in space. At the heart of this frenzy lies one of the hottest stellar remnants ever recorded, a white dwarf burning at a staggering 160,000 degrees Celsius. That's nearly 30 times hotter than the surface of our Sun, pumping out ultraviolet radiation so intense it strips electrons from atoms with brute force, making the nebula fluoresce in that signature electric blue. But what's truly astonishing is how this tiny, Earth-sized ember, no larger than a city, commands such a vast structure. The nebula's outer edges stretch over a light year, yet every atom within it dances to the tune of the white dwarf's radiation, glowing brighter where the star's light hits hardest and fading into near invisibility in the shadows. The blue flash's rapid expansion isn't just a spectacle, it's a forensic clue. Spectroscopic studies reveal the nebula's gases are laced with neon, argon, and even traces of sulfur, elements forged under extreme pressures in the star's core before being catapulted into space. These heavy elements shouldn't be so abundant in a typical planetary nebula, hinting that the progenitor star was far more massive than our Sun. Its death throws violent enough to dredge up material from layers normally left undisturbed. The nebula's outer halo, barely visible in optical light but glowing fiercely in infrared, tells another story, evidence of earlier, slower mass loss episodes, now overtaken by the faster-moving inner shell like a tsunami swallowing ripples. Then there's the nebula's asymmetry, a subtle but critical detail. While the overall structure appears spherical, high-resolution imaging reveals faint, jet-like protrusions along the polar axes, regions where gas streams outward even faster than the surrounding shell. These aren't random eruptions, they're likely shaped by the white dwarf's rotation or magnetic fields, funneling material into focused beams that punch through the nebula's chaos like cosmic blowtorches. Some astronomers speculate these jets might be the remnants of a binary companion's influence, its gravity sculpting the dying star's final breaths into these precision outflows before vanishing into the glare of the white dwarf. What makes the blue flash truly mesmerizing, though, is its youth. At just 3,000 years old, it's a planetary nebula in its infancy, offering astronomers a front-row seat to the instant aftermath of stellar death. The gases haven't had time to disperse or cool, the shocks haven't smoothed into equilibrium, and the central star still burns at near-peak intensity, its radiation etching new patterns into the nebula's glow even as we observe it. This isn't just a relic, it's a dynamic, evolving system where the physics of stellar demise plays out in real time, every ionized atom a testament to the universe's capacity for both violence and breathtaking beauty. As we watch the blue flash's luminous shell race outward, we're not just seeing a star's death, we're witnessing the birth of a cosmic recycler. Every heavy element surging through those expanding gases will one day seed new stars, new planets, perhaps even new life. And in that relentless expansion, there's a reminder, even in destruction, the universe is always building. NGC 6804, known as the Ring's cousin, isn't your typical planetary nebula. While most of these stellar remnants form perfect, symmetrical hoops of gas, this cosmic structure looks as if it's been crumpled by an invisible hand, its once pristine ring now warped and fragmented into jagged arcs. The disruption isn't random. This nebula's distorted shape tells the story of a violent encounter, a collision with interstellar material that's left its mark like a celestial scar. At first glance, the nebula's central region still hints at its original form, a faint, glowing ring of ionized oxygen and nitrogen illuminated by the white dwarf at its heart. But look closer and the symmetry unravels. The ring's eastern side flares outward, its edges frayed into tendrils that stretch into the void, while the western half appears compressed, as if shoved inward by some unseen force. This lopsided chaos isn't the work of the dying star itself. Instead, it's evidence of the nebula plowing through a dense patch of interstellar gas, the resistance sculpting its structure like wind shaping a dune. The interaction is written in the nebula's chemistry. Spectroscopic studies reveal abnormal concentrations of molecular hydrogen along the disrupted edges, a telltale sign of mixing between the nebula's ejected material and the cold, primordial gas of the interstellar medium. This isn't just a passive blending. The collision has triggered shock fronts, regions where gas heats to thousands of degrees as it rams into slower-moving debris. These shocks glow faintly in X-rays, invisible to optical telescopes but detectable as faint smudges of high-energy light. What makes NGC 6804 truly fascinating is its central star. Unlike the searing hot white dwarfs found in younger planetary nebulae, this one has cooled to a relatively mild 30,000 degrees Celsius. Its radiation is no longer strong enough to fully ionize the nebula's outer layers, leaving vast regions dim and ghostly. Yet the star's influence hasn't vanished entirely. Faint, fast-moving jets, vestiges of its earlier, more violent phase, still pierce through the chaos, their paths bent by the same interstellar winds that warped the nebula's ring. The real enigma lies in the nebula's age. Most planetary nebulae dissipate within tens of thousands of years, but the ring's cousin shows signs of being far older, perhaps 100,000 years or more. Its longevity suggests the interstellar material it's encountering isn't just distorting the nebula, it's also slowing its expansion, pressing against the gas like a cosmic brake. This resistance has given the nebula a strange duality. While its inner regions race outward at 20 kilometers per second, the outer edges crawl at less than half that speed, creating a layered, almost sedimentary structure. Then there's the matter of the filaments. Hubble's sharp vision reveals delicate strands of gas weaving through the nebula's fractured ring, some curling back toward the center as if pulled by invisible threads. These aren't remnants of the star's ejections, they're cosmic spider silk, gas from the interstellar medium caught in the nebula's gravitational web and drawn inward. Their presence hints at a future where the nebula, now a disruptor, will itself be absorbed, its atoms recycled into new stars and worlds. NGC 6804 isn't just a celestial oddity, it's a living lesson in impermanence. Here, in this warped ring, we see the universe's relentless cycle of destruction and renewal playing out on a scale both grand and intimate. And as we study its tangled gases, we're reminded that even the most beautiful cosmic structures are never truly static. They're transient artworks shaped as much by their surroundings as by the stars that birthed them. NGC 6891, the Diamond Ring Nebula, shimmers in the cosmos like celestial jewelry, its radiant central star blazing with such intensity it outshines the delicate, gossamer halo encircling it. This optical illusion isn't just poetic, it's a striking example of stellar physics in action. The nebula's namesake, ring, isn't solid, it's a shell of gas so thin, so meticulously sculpted by the dying star's winds, that it vanishes when viewed head-on, only to flare into visibility at its edges where light accumulates like a cosmic sleight of hand. At the heart of this spectacle lies one of the hottest white dwarfs known, a stellar remnant burning at a blistering 140,000 degrees Celsius. Its ultraviolet radiation doesn't just illuminate the surrounding gas, it annihilates it, stripping electrons from atoms with such force that the inner nebula glows electric blue, a visual echo of the star's ferocious energy. Yet step back and the nebula's true structure emerges. That iconic diamond ring effect comes from perspective, our line of sight compressing the nebula's spherical shell into a luminous hoop, its edges glowing brighter where our view passes through more material, while the central region appears hollow, dominated by the star's blinding glare. Hubble's razor-sharp vision reveals layers within the nebula's fragile shell. The innermost regions churn with turbulent knots and braided filaments, evidence of shockwaves where fast-moving stellar winds collide with slower ejecta. These structures glow predominantly in ionized oxygen, their vivid hues contrasting with the outer halo's softer nitrogen-rich emissions. That halo, stretching nearly 2 light-years across, tells a quieter story. Material expelled tens of thousands of years before the star's final collapse, now flourishing under the white dwarf's belated ultraviolet assault. But the real marvel is the central star's influence on the nebula's chemistry. Spectroscopy uncovers abnormal concentrations of neon and argon in the inner shell, elements forged deep in the star's core during its death throes and now being blasted into space. These heavy elements shouldn't be so accessible in a typical planetary nebula, hinting at violent mixing processes during the star's collapse. Even more puzzling are the fast low ionization emission regions, tiny, dense knots racing along the nebula's polar axis at speeds exceeding 100 kilometers per second. Their survival in this radiation-drenched environment defies expectations, suggesting magnetic fields or sheer density shield them from evaporation. The Diamond Ring Nebula isn't just a pretty cosmic bauble. It's a time capsule capturing a star's death in exquisite detail, from the turbulence of its final eruptions to the quiet unfurling of its earlier whispers. And as we study its luminous geometry, we're reminded that even the universe's most breathtaking illusions are rooted in the precise, unyielding laws of physics. NGC 6778, known as the bipolar butterfly, spreads its wings across space with a symmetry so precise it borders on mathematical perfection. This planetary nebula isn't just another glowing cloud. Its twin lobes arc outward like mirror images, each stretching nearly half a light-year from the central star, their edges glowing fiercely in ionized oxygen and nitrogen. But what makes this cosmic butterfly truly remarkable isn't just its beauty, it's the violent dance of forces that shaped it. Hidden in its heart lies a secret, not one star but two, locked in a gravitational embrace that may hold the key to the nebula's flawless form. The lobes themselves are anything but static. Hubble's sharp gaze reveals them as churning cauldrons of gas, their surfaces rippling with shockwaves where material ejected at different speeds collides. The northern lobe races outward slightly faster than its southern counterpart, a subtle asymmetry that hints at turbulence beneath the nebula's serene facade. Yet despite these internal storms, the overall structure remains eerily balanced, a feat that defies randomness. The prevailing theory, a binary star system, where the gravitational tug-of-war between two stellar partners funneled the dying star's final breaths into these opposing jets like a cosmic hourglass. Spectroscopic analysis supports this idea. The central star, or rather, stars emit light with peculiar Doppler shifts suggesting orbital motion. One is a white dwarf, its surface scorching at 80,000 degrees Celsius, while its companion remains shrouded in mystery, possibly a dim red dwarf or even a compact object like a neutron star. Their gravitational interplay wouldn't just guide the nebula's shape, it could also explain the waist of the butterfly, that pinched region where dense gas and dust form a torus around the binary pair. This donut-like structure acts as a nozzle, collimating the outflows into those pristine bipolar lobes, but the bipolar butterfly hides deeper puzzles. Near the base of each lobe, astronomers have detected strange, knotty structures, clumps of gas denser than their surroundings, some trailing comet-like tails. These aren't random debris, they're shaped by the star's magnetic fields, which twist and channel the outflow into intricate patterns. Radio observations reveal faint synchrotron emission along the lobe's edges, direct evidence of charged particles spiraling along magnetic field lines. It's as if the stars didn't just eject gas, they imprinted it with invisible cosmic blueprints. Then there's the matter of chemistry. While most planetary nebulae glow predominantly in hydrogen and helium, NGC 6778's lobes are unusually rich in neon and sulfur, elements forged deep in the progenitor star's core. This anomaly suggests the dying star wasn't just shedding its outer layers, it was dredging up material from its nuclear furnace, flinging it into space with violent convulsions. The southern lobe, in particular, shows enhanced nitrogen emissions, hinting at uneven mixing during the star's death throes. What makes this celestial butterfly truly extraordinary is its youth. At just 5,000 years old, it's a stellar infant, its lobes still expanding into pristine interstellar space. This gives astronomers a rare chance to study the earliest phases of bipolar nebula formation, watching physics sculpt gas into art in real time. And as we unravel its secrets, we're reminded that even the most perfect symmetry in space often arises from the most chaotic of dances, a testament to the universe's ability to forge order from chaos, one binary orbit at a time. NGC 6803, the miniature ring, may be small in size, but its cosmic punch is anything but modest, spanning a mere fraction of a light year. Barely a cosmic speck compared to sprawling nebulae like the Helix. This dense, glowing hoop packs an astonishing amount of stellar drama into its compact frame. What it lacks in scale, it makes up for in intensity, with a central star evolving so rapidly it's rewriting our understanding of stellar death in real time. At first glance, the miniature ring appears deceptively simple, a near-perfect, smoke-like circle floating in the void. But Hubble's razor-sharp imaging reveals intricate details that betray its violent origins. The nebula's inner edge isn't smooth. It crackles with microscopic knots and ripples, evidence of shock waves where the central star's supersonic winds slam into slower-moving gas ejected just centuries earlier. These collisions superheat the material to millions of degrees, making the ring's inner rim glow fiercely in X-rays, a rare trait for such a small planetary nebula. Then there's the star itself, a white dwarf so young and energetic it behaves more like a cosmic toddler than a serene stellar remnant. Surface temperatures exceed 120,000 degrees Celsius, and its ultraviolet radiation doesn't just ionize the surrounding gas. It obliterates molecular bonds, stripping atoms bare and forcing them to recombine in a frenetic light show. Spectroscopy reveals something even more startling. The star's luminosity fluctuates unpredictably, flickering like a candle in a draft. Some astronomers theorize these pulses come from residual nuclear burning on its surface, helium shells reigniting in sporadic fusion spasms. while others suggest a hidden companion star's gravitational tugs are stirring the embers into erratic brilliance. But the real enigma lies in the nebula's chemistry. Unlike most planetary nebulae where oxygen emissions dominate, the miniature ring's gas is unusually rich in neon and argon elements typically forged under extreme pressures deep in a star's core. Their abundance here suggests the progenitor star was massive enough to dredge up material from layers normally left undisturbed during a sun-like star's death. Even more puzzling are the crystalline silicates detected in the nebula's faint outer halo, dust grains that should have been vaporized by the white dwarf's radiation. Their survival hints at magnetic fields or dense clumps shielding them like microscopic bunkers. What truly sets NGC 6803 apart is its breakneck evolution. Most planetary nebulae change over millennia, but this one transforms on a human timescale. Comparisons between Hubble images taken just 15 years apart show measurable expansion, the inner rim racing outward at over 30 kilometers per second, its structure subtly distorting as it plows into interstellar material. This isn't just a dying star's aftermath, it's a stellar explosion caught in freeze frame, offering astronomers a front-row seat to physics that usually unfolds too slowly to witness. The miniature ring isn't just a celestial curiosity, it's a challenge to our assumptions. How did such a small nebula form around what was likely a hefty star? Why does its chemistry defy typical planetary nebula patterns? And what cosmic forces are driving its central star's wild mood swings? Every observation peels back another layer, proving that sometimes the universe's most profound mysteries come in the smallest packages. NGC 6720, the Ring Nebula isn't just a celestial icon, it's a cosmic magic trick. From our vantage point, it appears as a perfect smoke ring suspended in space, a glowing donut of gas floating against the void. But this is no simple hoop. Hubble's razor-sharp images reveal a far more intricate structure, a 3D labyrinth of gas expanding outward like a shimmering soap bubble, with our line of sight slicing straight through its center. The ring we see is actually the brightened edge of a spherical shell, where our perspective compresses more glowing material into view, while the hollow center peels back the curtain on the dying star's violent performance. At the heart of this spectacle lies a white dwarf, its surface scorching at over 120,000 degrees Celsius, so hot it emits most of its light in the invisible ultraviolet spectrum. This radiation doesn't just illuminate the surrounding gas, it transforms the nebula into a fluorescent masterpiece. Oxygen atoms, stripped of their electrons by the star's fury, glow electric blue as they desperately recapture lost particles. Nitrogen, less brutally ionized, paints the outer fringes in softer reds and oranges. The result, a celestial bullseye where chemistry and light conspire to create one of the cosmos' most recognizable artworks. What makes the Ring Nebula truly mesmerizing is its hidden depth. Far from a flat disk, it's a torus, a donut-shaped shell with a distinctly hollow center. The thickest part of this torus, the ring we see, is where the expelled gas piles up like waves against a cosmic shore. Meanwhile, faint, elongated lobes stretch above and below the main structure, evidence of faster-moving material jetting from the star's poles during its death throes. These protrusions, visible only through long exposure imaging, hint at a chaotic collapse where the star didn't shed its skin evenly, but in fits and starts sculpted by unseen forces like rotation or magnetic fields. Then there's the matter of scale. The nebula spans roughly 1 light-year across, but its gas is astonishingly sparse. Just a few dozen atoms per cubic centimeter, a vacuum by earthly standards. Yet that tenuous material catches the central star's light with breathtaking efficiency, glowing fiercely where the ultraviolet bombardment is most intense. Infrared observations uncover another layer, delicate tendrils of dust woven through the gas, their presence a puzzle. How did these microscopic grains survive the star's scorching radiation? Some theories suggest they formed late in the ejection process, condensing like frost in the nebula's cooler outer regions. Perhaps the most astonishing revelation comes from the nebula's motion. By comparing Hubble images taken 15 years apart, astronomers have tracked the ring's expansion in real time, its gases racing outward at 30 kilometers per second, fast enough to cross the continental United States in under a minute. This isn't a static monument, it's a dynamic event unfolding over millennia but perceptible across human lifetimes. The central star, meanwhile, continues to evolve, its ultraviolet output slowly fading as it cools into oblivion. The Ring Nebula isn't just a pretty cosmic bauble. It's a time capsule preserving the final moments of a star's life with startling clarity. Every ripple in its gas, every chemical gradient, tells a story of nuclear furnaces winking out, of gravity's grip loosening, and of stellar material returning to the void, destined to one day fuel new stars, planets, and perhaps even life. And as we study its luminous layers, we're reminded that even the universe's most iconic shapes are fleeting beauty written in smoke, destined to disperse. NGC 7354, the cosmic bullet, fires through space with a violence that defies its delicate appearance, a planetary nebula where gas races outward in supersonic projectiles, each one a frozen snapshot of stellar fury. Unlike the serene rings of the Helix or the symmetrical wings of the Butterfly Nebula, this cosmic structure is a battlefield, its layered shells pockmarked by high-speed bullets of material hurtling at nearly 150 kilometers per second. These aren't mere gas clouds, they're celestial shrapnel, dense knots of nitrogen and oxygen forged in the dying star's core and catapulted into the void like ammunition from a cosmic rifle. Hubble's images reveal the chaos in stunning detail. The nebula's outermost shell glows a faint ruby red, an expansive shroud of hydrogen ejected tens of thousands of years before the star's final collapse. Closer in, the gas tightens into a sapphire blue ring, its edges rippling with shockwaves where younger, faster ejectors slam into older debris. But the real spectacle lies deeper still, the bullets, each one larger than our solar system, streaking through the nebula's heart like tracer fire. Some leave glowing wakes, their paths etched in ionized helium. Others cluster in arc-shaped formations, suggesting periodic eruptions from the central star. At the core of this maelstrom sits a white dwarf unlike any other. While most stellar remnants emit steady radiation, this one flickers erratically, its surface temperature swinging between 80 and 120,000 degrees Celsius over mere decades. Astronomers suspect the star isn't just cooling, it's convulsing, with residual nuclear burning on its surface triggering thermal pulses that launch new volleys of gas into the surrounding nebula. These outbursts don't just feed the bullets, they sculpt the nebula's layered anatomy. Each shell corresponds to a distinct eruption, with chemical fingerprints revealing the star's evolution. Outer layers rich in hydrogen from its red giant phase, inner shells laced with heavier elements dredged up during its death throes. The bullets themselves are a cosmic puzzle. Spectroscopy shows they're denser and cooler than their surroundings, with some containing molecules that should have been obliterated by the white dwarf's radiation. One theory suggests magnetic fields coil around these clumps like protective cages, shielding their cores from disintegration. Another proposes they're the remnants of swallowed planets or asteroids, their rocky nuclei providing anchor points for gas to accumulate. Either way, their survival in this inferno hints at unseen forces, cosmic physics playing out on scales we're only beginning to map. Perhaps most astonishing is the nebula's youth. At just 5,000 years old, the cosmic bullet captures the instant after a star's demise, its structure still evolving as shocks ripple through the gas. Radio telescopes have even detected faint maser emissions near the bullet's microwave lasers generated by molecules vibrating in the turbulent environment. It's as if the nebula is still ringing from the star's death knell, its echoes carrying secrets of how stars recycle their essence back into the universe. NGC 7354 isn't just a relic, it's a celestial crime scene where every shell and projectile tells a story of violence, resilience, and the beautiful chaos that follows when a star breathes its last. And as we piece together its clues, we're reminded that even in destruction, the cosmos writes its history in light, speed, and fire. NGC 7026, the checkmark nebula, slashes through the cosmos like a celestial punctuation mark, its jagged, tick-shaped silhouette defying the graceful curves of most planetary nebulae. This isn't just a dying star's farewell, it's a violent scribble written in stellar winds and radiation, a cosmic afterthought that refuses to fade quietly. At its heart rages a wolf-rayet star, one of the universe's most volatile stellar archetypes, shredding its own remains into this chaotic geometry. Unlike the serene white dwarfs that illuminate most planetary nebulae, this progenitor is a maelstrom of fury, blasting out material at speeds topping 2,000 kilometers per second, fast enough to cross the Atlantic Ocean in the blink of an eye. What makes the checkmark's shape so striking is the physics behind its asymmetry. Most planetary nebulae start spherical, only to be sculpted into complex forms by binary companions or magnetic fields. Here, the wolf-rayet star's extreme winds act like cosmic sandblasters, carving cavities into the surrounding gas with reckless abandon. The nebula's eastern wing arcs sharply, its edge glowing fiercely in ionized oxygen where shockwaves compress and heat the gas. The western side, meanwhile, appears stunted and knotted, as if the star's eruptions came in uneven bursts, leaving behind a lopsided wreckage of its own demise. Hubble's close-ups reveal the turmoil in granular detail filamentary structures woven through the nebula like tangled wires, each one a fossilized echo of colliding stellar winds. Spectroscopy unveils even stranger details. The checkmark's gas is laced with carbon and oxygen, as expected, but also carries traces of neon and sulfur elements typically forged under extreme pressures deep in a massive star's core. Their presence suggests the wolf-rayet progenitor didn't just shed its outer layers, it dredged up nuclear ash from its own furnace, flinging it into space like a cosmic chef tossing ingredients into a boiling pot. Even more baffling are the knots, dense clumps of gas dotting the nebula's arms, some trailing comet-like tails. These knots shouldn't survive the star's radiation onslaught, yet they persist, possibly shielded by magnetic fields or their own sheer density. The real enigma lies in the nebula's youth. At just 3,000 years old, the checkmark is a stellar infant, its structure still evolving as faster-moving ejecta overtake slower debris. Radio observations detect faint synchrotron emissions along its edges, evidence of electrons spiraling along magnetic field lines at near light speed. This hints at invisible forces shaping the chaos, like ghostly hands sculpting smoke. Meanwhile, the central star continues to defy expectations. Wolf-rayet stars are notoriously short-lived, and this one's flickering brightness suggests it's on the verge of collapsing into a supernova. When it does, the checkmark may be obliterated in the blast or transformed into something even more extraordinary. NGC 7026 isn't just a nebula. It's a snapshot of stellar violence suspended mid-eruption, a reminder that even in death the most massive stars don't fade. They explode, they writhe, and they leave behind signatures too bold to ignore. And as we decode its jagged contours, we're not just studying a celestial object. We're reading a fiery footnote in the universe's grand narrative, one written in wind, radiation, and defiance. NGC 5315 isn't just another planetary nebula, it's a cosmic riddle written in gas and starlight. At first glance, it resembles a shattered diamond, its luminous shards arranged in a perfect X-shape that defies conventional explanations. Most dying stars eject their outer layers in spherical shells or bipolar jets, but this structure's sharp, intersecting arms suggest something far more peculiar. a star that somehow erupted along two distinct axes simultaneously, as if torn between competing forces during its final moments. The X's arms aren't mere optical illusions. Hubble's images reveal them as bona fide physical structures, tubes of ionized gas stretching over half a light year, glowing blue-green from oxygen and nitrogen emissions. Each arm moves outward at different speeds, with the northwestern limb racing ahead at 50 kilometers per second, while its southeastern counterpart lags slightly, creating a twisted, almost helical distortion in the nebula's overall shape. This velocity mismatch hints at episodic eruptions where the star's death throes came in staggered bursts, each outburst punching through the previous ejector like bullets through smoke. But what could launch gas in such precise, orthogonal directions? The leading theory points to a binary star system where two stellar partners orbit closely enough to sculpt the outflows. Imagine a spinning top wobbling as it loses momentum. The gravitational interplay between the stars might cause the dying star's expulsion to precess, its ejection axis shifting over time. Alternatively, the star's own magnetic fields could be the architects. Some models suggest powerful magnetic torques might have split the outflow into dual cones, channeling gas along rigid lines like water through a cosmic sprinkler. The real enigma lies in the nebula's core. Spectroscopy uncovers a central star so hot over 80,000 degrees Celsius it emits virtually no visible light, blazing instead in ultraviolet wavelengths that bleach nearby gas of its electrons. Yet the X's arms glow unevenly, with pockets of cooler, molecular hydrogen stubbornly persisting in their densest regions. These knots shouldn't survive the radiation onslaught, yet they do, possibly shielded by tangled magnetic fields or their own sheer mass. Even more baffling are the faint, filamentary bridges connecting the arms' delicate threads of gas that suggest unseen forces knitting the chaos into order. Then there's the matter of time. At just 3,000 years old, NGC 5315 is a nebula in its infancy, its structure still evolving as faster gas overtakes slower debris. Radio observations detect faint maser emissions near the armtips, microwave lasers generated by water molecules vibrating in the turbulent environment. These emissions act as cosmic speedometers, revealing shock fronts where supersonic winds collide with interstellar material. The data suggests the X shape isn't static. It's a snapshot of violence frozen mid-eruption, its arms still stretching, twisting, and reshaping themselves under the central star's unrelenting fury. What makes this nebula truly extraordinary isn't just its geometry, it's the window it offers into stellar death's most chaotic moments. Most planetary nebulae smooth into symmetry over millennia, their asymmetries erased by time. NGC 5315, with its crisp X, captures the instant when physics itself seems to hesitate, when a star's final act becomes a tug of war between rotation and magnetism, between order and chaos. And as we decode its luminous arms, we're reminded that even in the universe's most violent ends, there's a precision that borders on artistry. NGC 5882, the Southern Crab Nebula, sprawls across the cosmos with an eerie elegance, its delicate, claw-like extensions stretching into the void like a celestial crustacean frozen mid-motion. At first glance, this planetary nebula appears almost ghostly, its faint glow a stark contrast to the vibrant fireworks of younger stellar remnants, but don't let its subtle luminosity fool you. This cosmic crab is the aftermath of a star's violent rebellion, a slow-motion explosion sculpted by forces so extreme they've left permanent scars in the fabric of space. What makes this nebula truly mesmerizing are those symmetrical, crab-like arms, two faint loops of gas curving outward from the central star, each one a fossilized echo of supersonic stellar winds. Hubble's razor-sharp vision reveals these arms aren't smooth ribbons. They're studded with microscopic knots and braided filaments, evidence of shockwaves where fast-moving ejecta plowed into slower debris. The result is a structure that looks less like a shell and more like a cosmic fingerprint, its intricate walls encoding the star's death throws in luminous gas. At the heart of this spectacle lies a white dwarf star burning at nearly 50,000 degrees Celsius, a searing ember pouring ultraviolet radiation into its surroundings. But this isn't just any stellar remnant. Spectroscopic studies reveal its violent past. The star didn't shed its outer layers gently. Instead, it convulsed in episodic outbursts, hurling material outward in fits and starts. The southern crab's delicate arms are the aftermath of these eruptions, their symmetry suggesting the star's ejections were channeled along precise axes, possibly guided by magnetic fields or the gravitational tug of an unseen companion. The nebula's faintness tells another story. Unlike younger planetary nebulae that blaze with ionized oxygen and nitrogen, the southern crab's glow is subdued, dominated by hydrogen emissions. This hints at its age, roughly 10,000 years old, a point in stellar evolution where the central star's radiation has weakened enough that much of the expelled gas has cooled, reverting to neutral atoms. Yet even in this quieter phase, the nebula pulses with activity. Radio telescopes detect faint maser emissions near the tips of its arms, microwave lasers generated by water molecules vibrating in the turbulent gas. These masers act as cosmic speedometers, revealing expansion velocities of around 20 kilometers per second, a lingering whisper of the star's explosive past. The real enigma, though, lies in the nebula's chemistry. While most planetary nebulae are rich in helium and carbon, the southern crab's outer regions show unexpected traces of sulfur and argon elements typically forged deep in a star's core under crushing pressures. Their presence suggests the progenitor star was once far more massive than our Sun. Its death throws violent enough to dredge up material from layers normally left untouched. Even more puzzling are the dark lanes weaving through the nebula's arm's dusty filaments that somehow resist the white dwarf's radiation. Some researchers propose these are the remnants of swallowed planets or asteroids, their rocky cores shielding the surrounding gas from evaporation. But perhaps the most haunting detail is the nebula's impermanence. Already, the southern crab's outermost tendrils are dissipating into the interstellar medium, their atoms destined to be recycled into future stars and worlds. Yet within this fading glow lies a profound truth. Even in death, stars don't vanish quietly. They leave behind sculpted echoes of their final moments, cosmic monuments to the forces that shape the universe, one luminous claw, one shockwave, one atom at a time. NGC 6326, the cosmic hourglass, twists through space like a celestial timekeeper, its tightly pinched waist separating two vast glowing lobes, each one a reservoir of stellar material racing into the void. This isn't just another bipolar nebula. It's a masterclass in cosmic sculpting where invisible forces have taken a dying star's final breath and molded it into a near-perfect hourglass. The secret behind this dramatic shape, a combination of supersonic stellar winds and the star's own magnetic fields, woven together in a gravitational tug of war that leaves the nebula's midsection cinched like the waist of a cosmic corset. At the heart of this spectacle lies a white dwarf, its surface scorching at 60,000 degrees Celsius, hot enough to strip electrons from atoms with a mere glance. But the real star of the show is the nebula's structure. Those twin lobes, each stretching over half a light year, glow in vivid blues and greens, their gas ionized by the star's ultraviolet fury. The pinch at the center, though, that's where the magic happens. This narrow bridge spans just a fraction of that distance, a bottleneck where gas and dust have been compressed into a dense torus or donut-shaped ring. Hubble's sharp vision reveals this torus isn't just passive debris, it's a dynamic barrier deflecting the star's winds outward like a cosmic nozzle, forcing them to flare into those iconic lobes at the poles. But the hourglass illusion isn't just the work of gas dynamics. Spectroscopy uncovers a hidden puppet master. The star's magnetic field, thousands of times stronger than Earth's, twisting the nebula's shape like invisible fingers shaping clay. Imagine a star spinning rapidly as it dies, its magnetic field lines whipping outward like a high-voltage spiderweb. These fields channel the star's expelled material along rigid paths, creating those collimated jets that carve the nebula's bipolar structure. Radio observations reveal even more: faint synchrotron radiation along the lobe's edges, a telltale sign of electrons spiraling along magnetic field lines at relativistic speeds. It's as if the star's magnetism didn't just guide the nebula's formation, it left its fingerprints in the very light we see today. Then there's the matter of the waste itself. Unlike smoother planetary nebulae, the cosmic hourglass's pinch is riddled with microscopic knots and braided filaments, evidence of turbulence where the star's magnetic field interacts with its own expelled material. Some of these knots glow brighter in nitrogen emissions, suggesting they're denser clumps of the star's cooler outer layers, somehow surviving the radiation onslaught. Others streak outward in tiny jets, hinting at sporadic outbursts during the star's death throes. The real enigma, though, is the nebula's asymmetry. While the northern lobe expands at a steady 40 kilometers per second, the southern lobe races ahead slightly faster, a discrepancy that hints at uneven magnetic pressures or perhaps the gravitational nudge of an unseen companion star. Infrared imaging deepens the mystery, revealing a faint, spiral-shaped pattern etched into the lobe's inner walls. Some researchers believe this spiral is a fossilized record of the central star's precession, a slow wobble in its rotation axis as it collapsed, its magnetic field dragging the outflow along like a cosmic lasso. What makes NGC 6326 extraordinary isn't just its beauty, it's the window it offers into the invisible forces shaping the universe. Here, in this glowing hourglass, we see magnetism's power to sculpt chaos into symmetry, to turn a star's death into a timeless cosmic metaphor. And as we study its luminous curves, we're reminded that even in the vacuum of space, nothing escapes the pull of unseen hands twisting, guiding, and leaving behind art where there was only fire. NGC 6439, the Spiral Shell Nebula, swirls through space like a cosmic fingerprint, its delicate, coiled patterns etched into glowing gas with a precision that defies the chaos of stellar death. At first glance, this planetary nebula appears to pulse with concentric waves, each ripple a frozen echo of the dying star's final convulsions, but these aren't random undulations. Hubble's razor-sharp images reveal the truth. The nebula's outer layers are sculpted into a near-perfect spiral, a celestial vortex stretching over a light year across. This isn't the work of a solitary star fading quietly into the night. It's the signature of a hidden cosmic dance where gravity and motion have choreographed one of the universe's most mesmerizing goodbyes. The spiral's secret lies in duality. Most planetary nebulae form spherical or bipolar shapes, their structures shaped by a single star's death throes. NGC 6439's intricate coils, however, betray the presence of a silent partner, a binary companion whose gravitational pull has twisted the dying star's ejector into this cosmic whirlpool. Imagine a sprinkler spinning on a lawn, each rotation imprinting a new curve in the outflow. That's essentially what's happening here, except instead of water, it's star stuff being woven into this luminous helix over millennia. The binary stars orbit each other every few hundred years, their gravitational waltz sculpting the expelled gas into these precise, concentric rings, a fossil record of their orbital cycles written in light. Spectroscopy unveils even more complexity. The nebula's spiral isn't uniform. Its arms glow unevenly, with brighter regions marking denser ejections and darker gaps tracing quieter periods of mass loss. This variation isn't random, it's a chemical timeline. The outer coils, rich in nitrogen, represent material shed during the star's early death throes, while the inner turns blaze with oxygen, evidence of later, more violent eruptions. Radio observations detect subtle Doppler shifts in these arms, confirming they're not static sculptures but dynamic structures. still expanding outward at 20 kilometers per second. The spiral isn't just a shape, it's a stellar diary, its pages inscribed with the star's temperature fluctuations, eruption intensities, and even hints of its companions' gravitational nudges. Then there's the central engine itself, a white dwarf searing at 70,000 degrees Celsius, its ultraviolet glare ionizing the surrounding gas into vivid blues and greens. But the real intrigue lies in its flickering brightness. Unlike steady stellar remnants, this white dwarf pulses erratically, its luminosity swinging by 10% over mere decades. Some astronomers attribute these fluctuations to residual nuclear burning on its surface, helium shells reigniting in sporadic fusion spasms, while others suspect the gravitational tugs of its binary partner are stirring the star's embers into fits of brilliance. Either way, the star's instability adds another layer of drama to the nebula's spiral, its flickering light casting shifting shadows across the gas like a cosmic strobe. What makes the spiral shell truly extraordinary are the knots studding its arms, dense clumps of gas, each larger than our solar system, glowing ruby red in hydrogen alpha light. These aren't passive debris, they're racing outward at 40 kilometers per second, their surfaces evaporating under the white dwarf's glare while their cores cling stubbornly to molecules that should have been obliterated. How do they survive? High-resolution imaging hints at magnetic fields cocooning these knots, their invisible lines of force acting like cosmic armor against the radiation storm. Others propose the knots are the remnants of swallowed planets or asteroids, their rocky cores shielding pockets of gas from disintegration. The nebula's youth adds urgency to its study. At just 5,000 years old, the spiral shell is a stellar infant, its structure still evolving as faster-moving inner ejecta collide with slower outer coils. Infrared telescopes have even detected dust grains, crystalline silicates woven into the spiral's arms, materials that typically form in the cool atmospheres of red giants. Their survival here, in the heart of a radiation inferno, suggests they are shielded by the very density of the spiral's twists like treasures locked in a labyrinth. NGC 6439 isn't just a nebula, it's a celestial Rosetta Stone. Every coil, every knot holds clues to binary star dynamics, magnetic field interactions, and the delicate physics of stellar mass loss. And as we unravel its spirals, we're not just decoding the death of a star. We're witnessing the universe's quiet genius turning gravity's pull into art, one orbit at a time. NGC 6565, the blue vortex, spins through the cosmos like a celestial whirlpool, its luminous ribbons of gas twisting into hypnotic spirals, as if some unseen force had stirred the dying star's remains into a cosmic whirlwind. This isn't just another planetary nebula. It's a dynamic laboratory where radiation and motion collide, sculpting gas into shapes so fluid they seem almost alive. At its heart, a white dwarf burns at temperatures exceeding 80,000 degrees Celsius, its ultraviolet fury ionizing the surrounding material into a vivid azure glow. But the real magic lies in the nebula's motion. Hubble's time-lapse observations reveal the gases aren't just expanding outward. They're rotating, caught in a slow-motion vortex that defies simple explanations. The vortex's spiraling arms trace a story of hidden forces. While most planetary nebulae expand in orderly shells, the blue vortex's gases churn with turbulent eddies, their paths warped by the central star's radiation pressure and magnetic fields. Imagine a spoon dragging through honey. The dying star's energy doesn't just push the gas away, it twists it, creating swirling currents visible in the nebula's braided filaments. Spectroscopy uncovers even more drama. The inner regions whirl faster than the outer layers, a velocity gradient suggesting the star's spin. Or perhaps a binary companion's gravitational tug imprinted this rotation onto the ejected material. The result, a nebula that doesn't just glow, it moves, its structure frozen mid-spiral like a cosmic fingerprint. Then there's the matter of radiation's role. The white dwarf's ultraviolet onslaught doesn't just light up the gas, it shapes it. The nebula's brightest regions align with the star's rotational axis, where radiation punches through thinner gas, while denser equatorial material resists, casting shadowy lanes that amplify the vortex illusion. This interplay creates stark contrast zones of intense ionization glow electric blue, while cooler, nitrogen-rich pockets smolder in deep purples. Even the vortex's eye, a faint central void, isn't empty. It's a cavity carved by the star's relentless winds, where gas has been blasted aside to form this eerie calm at the storm's center. But the blue vortex's true enigma lies in its youth. At just 5,000 years old, it's a stellar newborn, its dynamics still unfolding. Radio telescopes detect maser emissions near the spiral's tips, microwave lasers generated by water molecules vibrating in the turbulent gas. These emissions act as cosmic speedometers, revealing shock fronts where the nebula's supersonic winds collide with interstellar material. Yet despite this violence, the vortex's structure remains eerily intact, a testament to magnetic fields' invisible scaffolding. Some researchers propose these fields act like cosmic threads, stitching the gas into this precise spiral even as it expands. What makes NGC 6565 extraordinary isn't just its beauty, it's the physics etched into every swirling arm. Here we witness a star's death not as chaos, but as controlled motion, a dance of radiation, gravity, and magnetism that transforms destruction into art. And as we unravel its luminous spirals, we're reminded that even in the void, the universe craves rhythm, spinning entropy into elegance one ionized atom at a time. NGC 6629, the Stingray's ghost, isn't just a planetary nebula, it's a cosmic chameleon, transforming before our eyes at a pace that defies the usual glacial timelines of deep space objects. When astronomers first studied it in the 1990s, it shone with the brilliance of a budding stellar remnant, its central star illuminating the surrounding gas in vivid blues and greens. But over mere decades, something extraordinary happened. The nebula began to fade. By the 2000s, Hubble's observations revealed a dramatic drop in brightness, a dimming so rapid it left scientists scrambling for explanations. This wasn't just a slow, inevitable cooling. It was as if the universe had flipped a switch, turning down the nebula's glow like a celestial dimmer. What makes the Stingray's ghost so mesmerizing is the sheer speed of its transformation. Most planetary nebulae evolve over thousands or even millions of years, their changes imperceptible across human lifetimes. But here, in the span of a few decades, a blink in cosmic terms, the nebula's central star cooled from a blistering 60,000 degrees Celsius to a comparatively mild 40,000. This thermal retreat had cascading effects. The star's ultraviolet radiation, once strong enough to ionize vast swaths of gas, weakened dramatically, allowing atoms in the nebula to recombine into neutral states. The result, a celestial light show fading into the shadows, its once electric hues dissolving into faint, ghostly whispers. Hubble's before and after images tell the story in stark detail. Early shots from the 1990s showcase a radiant, compact nebula, its gases churning with turbulent knots and braided filaments. Fast forward to 2016, and the same structure appears diluted, its edges blurring into the void as if the nebula itself is dissolving. Spectroscopy adds another layer of intrigue. Emission lines from ionized oxygen and nitrogen, once dominant, have nearly vanished, replaced by the subtler signatures of neutral hydrogen. It's as if the nebula is regressing in time, reverting to an earlier, quieter phase of stellar death. Yet the Stingray's ghost isn't just fading passively. Its central star, though cooling, remains restless. Recent observations detect flickers in its brightness, small but measurable fluctuations suggesting residual nuclear activity near its surface. Some researchers speculate the star might be reigniting in fits and starts, burning pockets of leftover helium in sporadic fusion bursts. Others propose a darker explanation. The star's outer layers might be collapsing inward, their weight compressing the core intermittently and triggering brief flare-ups. Either way, these flickers add a pulse to the nebula's twilight, like a heartbeat stubbornly pushing against the dark. The nebula's structure adds another puzzle. Unlike many planetary nebulae which expand steadily, the Stingray's ghost shows signs of contracting in certain regions. Radio measurements reveal inner shells of gas creeping backward at a few kilometers per second, as if recoiling from some unseen force. One theory points to the central star's cooling. As its radiation pressure drops, gravity gains the upper hand, tugging nearby material inward. Another idea involves magnetic fields, invisible lines of force snapping back like overstretched rubber bands dragging gas with them. Whatever the cause, this inward motion is rare, making the Stingray a living laboratory for studying how nebulae respond when their engines sputter. Perhaps the most haunting detail is the nebula's namesake shape. Its faint, wing-like extensions, reminiscent of a stingray silhouette, are now barely visible. Once glowing with the intensity of ionized helium, these structures have faded faster than the rest of the nebula, their delicate forms eroding into the interstellar medium. Infrared observations reveal why. The wings were always tenuous, their gas thinner and more vulnerable to the star's waning radiation. Their disappearance isn't just a loss of light, it's the unraveling of a cosmic sculpture, its artistry vanishing particle by particle. The Stingray's ghost challenges everything we thought we knew about stellar afterlife. It's proof that the universe doesn't always play by slow-motion rules, that sometimes change arrives not in eons but in years. And as we watch this nebula fade, we're witnessing more than a star's death. We're seeing the fragility of cosmic beauty, a reminder that even the grandest structures are fleeting, their legacies written in light that one day abruptly or gradually flickers out. NGC 6644, the cosmic keyhole, stares back from the depths of space like a portal to the unknown, a perfect circle of darkness ringed by fiery gas, as if someone punched a hole through the fabric of the nebula itself. This isn't just another planetary nebula, it's an optical illusion carved by cosmic forces, where a dense torus of dust and molecules aligns precisely with our line of sight, blocking the central star's light like a celestial stopper. The result, a keyhole so perfectly defined, it looks less like a natural phenomenon and more like a deliberate design. What makes this structure so mesmerizing is the contrast. The nebula's outer shell glows fiercely in ionized oxygen and nitrogen, painting the cosmos in electric blues and deep reds. But at its heart, the keyhole gapes a void so absolute it absorbs starlight instead of reflecting it. Hubble's infrared eyes, however, pierce through this darkness, revealing the hidden mechanics at play. The keyhole isn't empty, it's packed with cold, micrometer-sized dust grains, some laced with carbon and silicates, swirling in a dense disk around the central star. These particles are so thick, they absorb 99% of visible light, creating that eerie obsidian circle. Yet, ironically, this same dust glows warmly in infrared, radiating the heat it steals from the star's hidden glare. The keyhole's geometry is no accident. Spectroscopic studies show the dust torus isn't a flat disk but a warped funnel, its inner edges heated to hundreds of degrees by the white dwarf's ultraviolet fury. Meanwhile, the outer regions remain frigid, sheltering complex molecules like hydrogen cyanide and even water ice, materials that should be obliterated so close to a stellar remnant. This temperature gradient suggests the torus is dynamic, its particles constantly migrating. Some spiral inward to vaporize in the star's radiation, while others condense anew in the cooler outskirts, locked in a cosmic cycle of destruction and rebirth. But the real enigma lies in the keyhole's shadow play. The central star, though invisible in optical light, sculpts the nebula's glow like a lighthouse behind a curtain. Its radiation streams unimpeded above and below the dust torus, ionizing the gas into two luminous lobes that frame the darkness. From our vantage point, this creates a stunning illusion, a celestial iris with a pitch-black pupil, its edges sharpened by shockwaves where stellar winds collide with slower-moving ejecta. The effect is so precise, it reveals nuances often lost in other nebulae, faint, radial striations in the gas like spokes on a wheel, hinting at magnetic fields channeling the outflow into these disciplined patterns. Perhaps most astonishing is the keyhole's longevity. Most dust structures in planetary nebulae disperse within millennia, eroded by the central star's radiation. Yet NGC 6644's torus persists, its particles somehow resisting evaporation. Some researchers propose the dust is constantly replenished debris from comets or asteroids torn apart by the white dwarf's gravity, or even microscopic fragments of planets that once orbited the progenitor star. Others suggest magnetic fields trap the dust in place like cosmic flypaper. Either way, this resilience transforms the keyhole from a fleeting shadow into a cosmic fossil, preserving a record of the star's violent transition. The cosmic keyhole isn't just a celestial curiosity, it's a lesson in perspective, that perfect circle of darkness. It exists only because we're viewing the nebula head-on. Shift our angle slightly, and the torus would appear as an equatorial band, a reminder that the universe's most striking shapes often hinge on our place within it. And as we study this interplay of light and shadow, we're reminded that sometimes the most profound mysteries aren't in the stars themselves, but in what they choose to hide. NGC 6818, the Little Gem Nebula, blazes in the cosmos like a celestial jewel, its compact frame, packing an intensity that rivals nebulae 10 times its size. Spanning barely half a light-year, this planetary nebula punches far above its weight class, glowing with a brilliance that earned it its sparkling nickname. But what makes this cosmic gem truly dazzling isn't just its luminosity, it's the chemistry behind its vivid hues. The nebula's core shimmers in electric blue, a signature of doubly ionized oxygen atoms stripped bare by the central star's ultraviolet fury. These oxygen ions, robbed of 2 electrons, emit light at precise wavelengths, creating that signature sapphire glow visible across interstellar distances. Surrounding this blue heart, the nebula's outer layers transition into rich emerald and ruby tones, where nitrogen and hydrogen emissions take over. This chromatic gradient isn't just for show, it's a thermal map. The blue inner regions, superheated to tens of thousands of degrees, mark where the star's radiation hits hardest, while the cooler outskirts glow redder, their atoms less violently ionized. Hubble's sharp vision reveals even finer details, braided filaments and microscopic knots within the gas, evidence of shockwaves where fast-moving stellar winds collide with slower ejecta. Some of these knots, denser than their surroundings, stubbornly resist evaporation, glowing like tiny diamonds sewn into the nebula's luminous fabric. At the center of this spectacle burns a white dwarf star hotter than 60,000 degrees Celsius, a stellar ember so intense, it outshines entire galaxies in ultraviolet light. Yet despite its ferocity, the star appears deceptively faint in visible wavelengths, its light heavily absorbed by the nebula's own gases. This irony defines the little gem's allure. The same materials that obscure the star also amplify its brilliance, scattering and re-emitting its energy into the vibrant colors we admire. The nebula's small size adds another layer of fascination. Unlike sprawling structures like the Helix Nebula, where gases diffuse over light years, the little gem's compact dimensions concentrate its glow into a celestial spotlight. This density makes it a prime laboratory for studying ionization, fronts the razor-thin boundaries where the star's radiation transforms neutral gas into glowing plasma. Here, the physics of stellar death plays out on a human scale, with processes that might be diluted in larger nebulae appearing in stark, concentrated detail. But the real magic lies in the nebula's asymmetry. While its overall shape appears spherical, high-resolution imaging reveals subtle elongations, hints that the dying star's ejections weren't perfectly even. Some researchers attribute this lopsidedness to the star's rotation, its spin flinging material outward faster along the equator. Others speculate about a binary companion's gravitational nudge, gently warping the outflow like an unseen hand molding smoke. NGC 6818 isn't just a pretty cosmic ornament. It's a testament to how chemistry, radiation, and motion conspire to turn destruction into art. A reminder that even in the vastness of space, the most captivating wonders often come in the smallest packages. NGC 6884, the twisted ring, writhes through space like a cosmic serpent, its glowing loops of gas contorted into shapes so unnatural they defy simple explanation. This isn't the neat, symmetrical halo of most planetary nebulae. It's a labyrinth of luminous braids and kinked filaments, as if the dying star at its heart convulsed in erratic fits as it shed its skin. Hubble's razor-sharp images reveal the chaos in stunning detail. The nebula's main ring stretched and warped like taffy, while jagged tendrils burst outward at odd angles, some even curling back toward the central star as if pulled by invisible strings. The violence behind these distortions lies in the star itself, a white dwarf burning at nearly 50,000 degrees Celsius, its ultraviolet glare illuminating the nebula's tortured geometry. But what sets this stellar remnant apart isn't just its heat, it's the star's bizarre mass loss history. Spectroscopy uncovers shocking velocity disparities within the nebula's gases. Some regions race outward at 40 kilometers per second, while others crawl at half that speed, their trajectories skewed by explosive outbursts spaced unevenly over millennia. It's as if the star didn't die in a steady exhale, but in a series of violent coughs, each eruption punching through previous ejecta like bullets through smoke. Then there's the ring's infamous twist, a helical deformation that gives the nebula its name. This spiral distortion suggests the central star didn't just erupt erratically. It spun, its rotation flinging material outward like a malfunctioning cosmic sprinkler. Some astronomers attribute the twist to magnetic fields, their invisible lines channeling the star's dying breaths into these coiled patterns. Others propose a darker culprit, an unseen binary companion, its gravitational tugs warping the outflow like a puppeteer pulling strings. Supporting this theory are faint, knotty structures along the ring's inner edge, clumps of gas denser than their surroundings, possibly sheared into existence by a partner star's disruptive presence. Yet the real enigma lies in the nebula's chemistry. While most planetary nebulae glow predominantly in oxygen and nitrogen, the twisted ring's braided filaments blaze with unexpected neon and sulfur emissions, elements typically forged under extreme stellar core pressures. Their abundance here hints the progenitor star was far heavier than our Sun. Its death throws violent enough to dredge up material from layers usually left untouched. Even more baffling are the rogue knots, dense globules of molecular hydrogen embedded in the ring, their survival defying logic. Bathed in the white dwarf's radiation, these knots should have vaporized instantly. Their persistence suggests magnetic armoring or sheer density shielding them, like cosmic pebbles resisting a hurricane. The twisted ring's youth adds urgency to its mysteries. At just 5,000 years old, it's a stellar newborn, its structure still evolving as faster gases overtake slower debris. Radio telescopes detect faint maser emissions near its distorted edges, microwave lasers generated by water molecules vibrating in the turbulent gas. These emissions act as cosmic speedometers, revealing shock fronts where supersonic winds collide with interstellar material. The data paints a dynamic portrait, a nebula still reeling from its birth, its twisted rings not yet settled into the serene symmetries of older remnants. NGC 6884 isn't just a celestial oddity, it's a challenge to our understanding of stellar demise. Most dying stars shed their layers smoothly, their nebulae blooming into predictable shapes. But here, in this tangled glow, we see a star's death as chaos incarnate, a reminder that even in the void, nature reserves the right to rebel. And as we unravel its knotted filaments, we're not just studying a nebula. We're decoding the universe's capacity for beautiful, defiant disorder. NGC 7008, the Fetus Nebula, drifts through the cosmos like a spectral prenatal portrait, its uncanny biological silhouette glowing against the interstellar dark. The resemblance isn't poetic license. This planetary nebula's arched back, clustered knots mimicking limbs, and fluid-like tendrils create an almost unsettling mirror of early human development. But this celestial mimicry isn't guided by biology. It's sculpted by the violent interplay of radiation, stellar winds, and gravity's invisible hand. At the nebula's core lies a dying star in its final throes, a white dwarf searing at 50,000 degrees Celsius. Its ultraviolet fury bombards the surrounding gas, stripping electrons and forcing the material to fluoresce in haunting hues of red and blue. Yet the Fetus Nebula's form isn't just a simple shell, it's a labyrinth of structures. The most prominent arc, resembling a curved spine, is actually a shock front where fast-moving stellar winds collide with slower, older ejecta. This collision superheats the gas, making it glow fiercely in oxygen emissions, while the limb-like protrusions are dense knots of molecular hydrogen and dust resisting erosion, their silhouettes backlit by the star's relentless glare. What truly elevates this nebula from curious to extraordinary are the turbulent dynamics shaping its illusion. Hubble's close-ups reveal delicate filaments swirling through the nebula's body, like veins threading through tissue. These aren't static features, they're evidence of hydrodynamic instabilities, where pockets of gas with different densities interact, creating ripples and braids in the outflow. Some filaments even curve backward, suggesting the central star's radiation pressure or magnetic fields are funneling material into these eerie, organic shapes. The nebula's namesake, head region, adds another layer of intrigue. Spectroscopy reveals it's chemically distinct, richer in nitrogen than the surrounding gas, hinting that it originated from deeper within the progenitor star, dredged up during its chaotic collapse. This area also moves slower than the rest of the nebula, as if the star's death spasms expelled it in a separate, more sluggish eruption. Infrared observations uncover hidden complexity, dust grains, likely carbon-based, swirling in the head's shadowed recesses shielded from the star's scorching radiation. But perhaps the most spine-tingling detail is the nebula's asymmetry. Unlike the neat rings of younger planetary nebulae, the Fetus Nebula's structure is lopsided, its western side more elongated, as if stretched by unseen forces. Some astronomers attribute this to the dying star's motion through space, its trajectory creating a bow shock effect, like a boat plowing through water. Others propose the gravitational tug of an unseen companion star warped the outflow, leaving behind this ghostly, half-formed silhouette. NGC 7008 isn't just a cosmic Rorschach test. It's a testament to how chaos and physics can conspire to create echoes of life in the void, a reminder that the universe's artistry knows no bounds, even when painting with the ashes of dead stars. NGC 7662, the Blue Snowball, might seem like a textbook example of a planetary nebula at first glance, a serene, azure sphere floating in the cosmic dark. But peer closer, and this celestial orb reveals a hidden turbulence. Those delicate filaments and high-velocity knots streaking through its glow aren't just decorative flourishes. They're cosmic fingerprints, evidence of a dying star's violent tantrums frozen in time. Recent observations have peeled back the nebula's tranquil facade, exposing a dynamic heart where gas races outward at speeds that defy expectations, and mysterious structures called flyer defy destruction under the white dwarf's blistering radiation. The most striking of these enigmas are the flyer-fast low-ionization emission regions, dense, fast-moving clumps of gas erupting from the nebula's polar regions like cosmic geysers. Unlike the rest of the Blue Snowball, which glows fiercely in ionized oxygen, these structures emit light from lower energy states, suggesting they're cooler and more resilient than their surroundings. But here's the twist: they shouldn't exist. The central white dwarf, hotter than 60,000 degrees Celsius, bathes the nebula in ultraviolet radiation intense enough to obliterate molecular bonds. Yet these knots persist, hurtling outward at over 100 kilometers per second, their paths etched in hydrogen alpha light like luminous contrails. How do they survive? High-resolution spectroscopy reveals they're armored, shrouded in magnetic fields that act like invisible force fields, deflecting the star's radiation while their cores remain intact. Then there's the matter of their origin. One theory suggests they're remnants of the star's equatorial disk, material flung outward by violent outbursts during its death throes. Another proposes they're the cosmic equivalent of shrapnel debris from a swallowed companion star or planet, blasted into space during the progenitor's collapse. The most tantalizing clue comes from their chemistry. These flyer are rich in nitrogen and helium, elements forged deep in the star's core, hinting they were dredged up from layers normally untouched during a sun-like star's demise. It's as if the dying star, in its final convulsions, reached into its own furnace and scattered the ashes into the void. But the Blue Snowball's surprises don't end there. New infrared observations have uncovered faint, spiral-shaped structures woven through the nebula's outer halo, whisper thin tendrils of dust stretching far beyond the main glow. These aren't random debris, they're trails of material ejected tens of thousands of years before the star's final collapse, now illuminated like cosmic breadcrumbs. Their spiral pattern suggests the star didn't die quietly. It spun, its rotation flinging gas outward in rhythmic pulses, each eruption leaving a new coil in the nebula's expanding shroud. Some researchers even speculate these spirals might hold clues to a binary companion's gravitational nudges, its presence subtly warping the outflow into this intricate design. What makes NGC 7662 truly extraordinary is its defiance of time. Most planetary nebulae fade within millennia, their gases dissipating into the interstellar medium. But the Blue Snowball's flyer and spirals persist, their structures sharp against the cosmic backdrop. They're more than relics, they're active participants in the nebula's evolution, their motions still shaping the surrounding gas as they race outward. Every new observation peels back another layer, revealing a stellar demise far more complex and far more beautiful than we ever imagined. And as we study its luminous knots and ghostly spirals, we're reminded that even in death, stars don't just vanish. They leave behind puzzles written in light and velocity, waiting to be solved. From ghostly nebulae shaped like owls and jellyfish to galaxies that spin backward and stars wrapped in dark matter, these 50 NGC objects prove the universe is far stranger than we ever imagined. Each one defies expectations, whether it's the Helix Nebula's eerie eye staring back at us, the cat's eye's nested rings whispering of a star's rhythmic death throes, or the cosmic Christmas tree's festive stellar fireworks. These aren't just celestial landmarks, they're cosmic rebels, challenging the rules of physics and leaving astronomers with more questions than answers. Why does the Saturn Nebula's gas twist into perfect handles? How do the Blue Snowball's flyer survive their star's radiation storm? And what hidden forces sculpted the twisted ring's chaotic loops? The beauty of these objects lies not just in their mystery, but in their sheer diversity. Some, like the Jewel Bug Nebula, gleam with geometric precision, while others, like the Fetus Nebula, mimic earthly shapes through cosmic coincidence. There are stellar graveyards where white dwarfs pulse like erratic lighthouses, and nurseries where newborn stars carve pillars of dust into surreal landscapes. Every catalogue number hides a story of violence, rebirth, or forces we've yet to name. So grab a telescope or just step outside on a clear night, look up and wonder how many more cosmic oddities are waiting to be found. The NGC catalog is just the beginning, and if you've got a favorite celestial mystery, maybe one we missed, drop it in the comments. Let's keep the conversation as boundless as the cosmos itself. Don't forget to like and subscribe for more deep dives into the universe's weirdest wonders. The stars won't explain themselves, but together we can try